sensed it. My intuitive Calvin sense was a tingling. There you go. Okay. SHA256, our most beloved algorithm. Why is it our most beloved algorithm? SHA256 does this thing that I wish every single algorithm would do, which is that it's named algorithm. It's the secure hash algorithm. So many of these algorithms, like the max flow algorithm is named max flow. What does that mean? You have to already know what the algorithm is to understand what that means. And it's like, oh, there's a graph, and the graph has edge weights, and we see how, it's like, no one cares about any of that stuff. This is the secure hash algorithm. It is what it says it is, right? And you're like, I know what you're thinking. You're like, how much secure do you hash? 256, that's how much, right? And so this algorithm is great. Some of you have looked at the SHA256 homework already. Good for you. As you have noticed, this is an accidentally variable difficulty class, so you can always attempt to do the assignments before I tell you how to do them. No one will stop you, right? I did all of these assignments before anyone told me how to do it because I did the assignments, then wrote the slides, right? I had a great time. I was implementing RSA, which is the next algorithm after this, yesterday, and I was like, I always forgot that the reason I always throw out my code when I'm done with this is I like writing it in for the first time, every time, so I just stopped taking notes. You all have a lot of things going on in life, but it looked to me like just about all of you wrote macros just fine. Macros is fun. It's a little puzzle assignment, right? You think about it a little bit, and then you're done. In terms of course scheduling, the combination of plug, the apocalypse, having to cancel that class because of the snowstorm in the other state, means that I haven't seen you as much in this room as I would like to, which is the reason I'm not offering to take us to Rust PDX next week. But be advised, there are two things next week that usually you would be offered to go to. One of them is the Azure user group, and one of them is PDX Rust. Now, that means that 4 weeks or 5 weeks from next week, which is 6 weeks or 7 weeks from now, I will offer to go to one of those two things with you. So keep an eye out for Rust PDX. I feel actively bad I'm not teaching this class in Rust this term, as we were all just talking about. I tried very, very hard to learn Rust in 3 weeks, and it was not something that I could do. But there are, in fact, people that have been writing Rust for quite some time, and Bart Massey, who's in some way affiliated with PSU and in some way affiliated with Mozilla, who are the people that invented Rust. The only other systems programming language in the world, Swift doesn't count, C++ doesn't count. Actually runs the local user group and is one of the lead Rust architects, so that's not someone that I want to compete with. Versus, I probably write C code about as well as anyone in Portland. There's not a huge difference in the ability of people to write C. Okay, so today, as promised, in person, because it is definitely worth blowing one of our in-person days on this, no matter how few of them we have. We're going to go over SHA256 in person. Now, to fully take advantage of the in-person thing, you're supposed to start talking over me, raising your hand, shouting at me, raising questions, talking with your hands, and all of these things while I'm going over SHA256. And you'll want to be doing this because you'll keep being excited and being like, oh, that's so awesome every single time I do a slide, right? So that's what happened to me the first time I saw SHA256. It was actually when I made these slides. No one ever taught this to me. I just decided it was cool and started teaching it. And so when I decided to teach it to myself, I was like, I wish I could learn this from a slide deck. So I typed SHA256 slides into Google and found the best slide deck I've ever seen in my life. It was made by Saravana Vijayakumara. And actually, I didn't know that when I found the slide deck. I found one of this person's doctoral students that came to the United States to teach. This person teaches at IIT Bombay, which I'm assuming is the best school in the world because I've seen these slides, and I have also seen slides from MIT. And I have taught Indian students and asked them what they think of IIT Bombay, and they get this look on their face, it's the place, right? So this is one of the top technical schools in the universe. It is unlikely that any school in the United States will be able to catch up with the top couple Indian and Chinese schools in the next 20 years, no matter what we do. And this person just posts all of their material online for free. Now, not all that material is immediately useful to us. I'm not teaching us about zero-knowledge proofs this term. But if you want to learn about zero-knowledge proofs, you click that link and you find out about them, right? The degree to which I suddenly understood secure hash algorithm when I saw these slides is quite high. My slides are going to be slightly worse because I had to format them in the way that I can understand them. And so I'm sorry, I do not teach at the best technical school in the universe, but God willing, I will in 5 years. Okay, so why? So everyone knows what hashed browns are, right? You take some browns, you slice them, and how far deeply do you slice them? You slice them into their most atomic unit, the bit, right? So you slice them into bits of information. Then you take those bits of information and you put them in a cast iron pan. Are we all cast iron pilled here? We got gifted a cast iron for Christmas. It's the heaviest thing in my house. It weighs 4 times as much as my cat, right? Okay, so you have your browns, which are logically equivalent to bits. You put the bits in the pan, and then you do something roughly like this, right? And that's the macros assignment, right? Because we do macro motions to the atomic unit of information bits. Now, some of you may have noticed that sometimes you chop up a lot of potate, which is the singular of potato, and you put that potate in the cast iron pan, and then there's less mass when you're done, or perhaps volume, than when you started, right? And that's because hashing is a compression function. It takes much of something and returns little of something. And I've noticed that no matter how many browns I hash, I always eat 100% of them, which means no matter how many potatoes I start with, I always end with the same amount, which is exactly how many I want to eat, right? And in the case of SHA256, I want to eat 256 browns, and in the case of SHA512, I want to eat 512 browns, okay? There's some confusion on how much a brown is, right? And that's okay. Are the Browns a sports team from perhaps Cleveland?
Yes.
Go Browns? No? Okay.
They have like sex offenders that quarterback as well, so super not go Browns.
Okay.
There are worse teams to root for, I'm sure.
It doesn't seem like everyone else is sure.
No hate for the New England Patriots?
So I was going to ask about the Patriots. Are they worse than the Patriots?
Record-wise and morality-wise, probably. Yeah. Oh.
That's pretty impressive.
They wear like trash bags over their heads at games with their fans.
Go Browns. All right, so, and so we have 256 of them, right? Which is a lot of Browns to have, because apparently we don't even like the one we have. Okay. Unlike my hashes brown, which I always want to be exactly the same, which is perfectly crispy on the outside and perfectly fluffy on the inside, or however hash brown is supposed to be. I haven't cooked a hash brown in like 8 years, right? And I used to import them to North Carolina from Oregon, and then I moved to Oregon, and now I only eat Honeycrisp apples. I'm not sponsored, by the way. Don't. Okay. So unlike hashing browns, where we do scramble things up, we have a very specific intent of scrambling things in our secure hashing algorithm, which is we want each pile of potatoes to turn into a wildly divergent hash brown. We want to be able to tell if we see a pile of potatoes, if it corresponds to a specific hash brown, and we want to tell if someone made a single change to our pile of potatoes that we get completely different hash browns. And the reason for this is because our pile of potatoes encodes the Linux operating system, and we don't want someone to put something that is insecure in our Linux operating system, such as, I have to say something that's not ludicrously unappealing, but like you could put something that's poisonous in a pile of potatoes, right, and it would look much the same. But you would want to know if that thing that's bad for you is in the pile of potatoes anywhere, and you would do that by making hash browns and seeing that they look wildly different. So the goal of a good hashing function for bits, but not for potatoes, is that no matter what bits you start with, if you change a single one of them, the entire hash changes. And when I say the entire hash changes, what does that mean? That means at probability 50%, each bit changes. Now, we don't prove that exactly, and it would be a little bit too suspicious if exactly a 50% probability they changed each time. I'm going to show you a series of transforms and operations later in this class, and oftentimes by the end of that, people say, why do you do all of this stuff? We're trying to flip every bit with probability 50% based on changing any input bit. If we change all of the input bits, we should be flipping things at 50% probability many times. But we don't want there to be a correspondence or any predictability to what the hash brown looks like based on any change, no matter how small or how large. This is essentially arguing there should be no correlation between two things. We have a built-in non-cryptographic hash in our most beloved language, Python 3.12.5.
Is it worth asking why we want to flip the bit 50% of the time? Or will we get there?
It's related to this notion of wanting to be able to tell that something has been tampered with. But it's related in one additional step, which is that we don't want it to be easy for someone to tamper with it in a specific way to get the same hash back. So if I'm performing malware injection on an operating system naively, it would immediately change the bits. But if it changes only the lowest order bit, then I add other changes until it turns back into the original thing. So you want it to be hard for someone to mess with something and still have the same signature. So these are two different forms of security, and I did consider them out of scope for this class, but it is pre-image and collision resistance are the two types of things. And yes, the lab on those was canceled by the variety of snow days and things. But I'll put a link in Discord at some point. You can take a look at it. The class that this is like the great-grandchild of used that lab. Here is another reason to have everything change, which is not related to cryptography. It's related to this little thing called a hash table, or as we all call them, dictionaries. You all say hash map, don't you?
Object.
Okay. I think a hash map is a subset of objects, right? Yeah, okay. And probably in our least beloved language, Java, the hash map implements the dictionary interface. That's so much worse. So hash map implements map, which functions as a dictionary?
Yes.
I did make a slide deck on this once, but I managed to forget it. Thank you, Ari. I quickly implemented an example of a few hashes here in our most beloved language. And I got really annoyed, so I used a very complicated format string to force a signed bit on each one of my numbers so that they would line up neatly on the right-hand side. And what I want to show here is that these letters are something that we would often consider adjacent to each other. And I'm not, in fact, printing bits. I'm printing decimal numerals, right? Well, you'll notice that by changing a single letter in the string A, B, C, D, or E, thinking of those as 5 strings, because I'm looping over the individual characters, we get wildly divergent hashing values with different sign values. We do notice we get roughly the same number of digits, which means we have roughly the same bit significance, which means we're getting the same amount of hash browns back. Now, I'm not manipulating the amount of potatoes going into the hash browning function here, but in fact, if you start jamming random things inside a Python hash function, you'll notice you roughly get always the same size number back. This is one of the features of hashing functions. Why do we often use hashing functions in a data structures class, right? Well, what we want to do is we want to be able to throw a pile of things at the computer and say, hold on to these. And then we want to, if we know we have thrown a pile of things to the computer, say quickly, give me the thing with this name. And if you compute the hash of that name, and then you use the hash of that name to look up a location in a list, you look things up instantly. And if you search through the whole list, you look things up in the amount of time it takes to look through the entire list, whatever that amount of time is. Who loves LaTeX?
Yeah.
Yeah, that's what I thought, right. I'm an accidental LaTeX appreciator. You know, I tried really, really hard to write all of my formulas in HTML because I knew I was supposed to, right? And I was like, wow, this looks awful, and my head hurts. And so I started just writing LaTeX. And then I found out in just about every single markdown language on earth, not just including namebrand.md markdown, if you just slam LaTeX into it, this thing called MathJax loads inside your browser, and it talks to a cloud CDN that's maintained by someone for free, and it turns my beautiful this stuff, which is actually just as readable to me as this formula, because I've spent a little bit too much time studying formula mathematics. So anyways, someone's paying for a server that rendered this somewhere, and it's not me. So that's cool. I like to think of this as petty theft. So thank you. Everyone say thank you to petty theft for seeing this. This is an example of a hashing function. Okay, so what's this do? So we're going to say we're going to let m be the size of some hashing table. M stands for, of course, map, named after the map object in Java, which is implemented by the hash map. No. The map interface in Java, which is implemented by the hash map object. There we go. We got it. We got it in the second half, right? I know Java. There's a university that let me teach a class in Java, by the way. And those students actually may have known Java by the end of that semester. They also learned a lot of Bash. Okay, and what are we going to do? We're going to take A. A is a natural number. What are the natural numbers? Those are the numbers without signs. So I've deleted the pluses and minuses from this thing. Why have I done that? Well, Python programmers and just, can you use negative indices in JavaScript? Surely JavaScript doesn't let you do that.
You can only use it in slice.
Oh, but you can use it in slice. All right, so obviously that should be against the law, right? Like, you can't be a negative distance from something.
That too.
That sounded funny, but I didn't hear all of it. I'm sorry.
We just said nothing is against the law of JavaScript.
Oh, that's true, yeah.
JavaScript.
No, shout out JavaScript for that, actually. You know, like, I appreciate JavaScript unapologetically being itself, right? From time to time, I start writing some JavaScript, and I'm like, why am I not writing Python? Usually when I find out I'm not working with integers, which is the thing that always sends me back. So I have a natural number. And I denote that this natural number is smaller than the size of my map, and it is also co-prime with the size of my map. Why is that? Well, what I'm going to start to do at various points in this class is I'm going to start dividing one number by another number, and I'm always going to want to have a remainder. If this thing's co-prime, I can divide m by any multiple of a, and I will always have some remainder, which is good, because if I wasn't having some remainder, then I would be getting 0 every time, and then I would be loading up the 0th element of my array with multiple elements, and that's the bad thing we're trying to avoid. So when I'm computing a hash, I frequently want things to be co-prime. So I'm going to take two positive co-prime numbers, and some of them are going to be bigger than others. And so we claim then that any integer value x can be mapped onto the integers modulo m, which are the values from 0 up into 1 minus m. Well, notice I'm oscillating between the natural numbers and the integers here. I'm allowed to do that because I'm a computer scientist and I don't use negative values. But I'm also doing modular arithmetic, which is forcing everything to have a positive sign. If I do the modular arithmetic in Python, if I do it in C, it's a remainder, and so you have to write the special C remainder operation that converts it into modulo, which we all remember from Enigma. Oh, yes, looping back on Enigma. I realized something quite recently that I should have said to all of you a long time ago. Many of you successfully implemented Pythonic mod in C for Enigma. That's all well and good. The clever solution was to subtract 26 from your A constant, and so things are always offset by exactly 26, so all of your values were necessarily positive because you were always modularly updating by 26, so you could have saved a large number of operations and a large number of headaches. So anyways, from time to time you should just add the base to something, and that forces it to be positive. Moving on. Okay, so what is this thing? We're going to take our input value x, any integer value x. We're going to multiply it by the co-prime value. Then we're going to divide it by m and take the remainder. So this thing is less than m. And if I increase this by 1, I increase this by an unpredictable amount, right? Because I don't know if I'm going to increase by a or some arbitrary value when I divide by m. So I cannot predict whether this value is going up or down each time, right? I'm going to divide that by w. Oh, that's supposed to be m as well, probably. I updated these slides to remove some omitted values, and all of these w's should be m's. They're just flipped upside down, that's the problem. We're going to divide that by m, multiply by m. You don't have to do any of that stuff. We just multiply the co-prime value by x, and then we take a modular division. That means that you always get an output that is in this range, and and you get an output that you cannot tell if when you increase x by 1, whether you get a higher or lower number.
So doesn't multiplying by m and dividing by m do that?
Yes.
Okay.
And in fact, because I have these open, we can find this and update the slides. And I don't even think I need the floors, right? Look how small my monitor is. Look at, I have no idea what I'm looking at. Okay. What does left do? I think I can get rid of all this stuff. Missing argument for frac. Oh, it doesn't even need to be a fraction anymore. Also, one of the undergraduate math majors said I should include some of these things in parens. Okay. There you go. Okay. And then we're also going to change this to m. Oh, I got some of them, but not all. Okay. Oh, it's still thinking. My computer's slow, is what's happening. This is slide 9. I don't know how long it's going to take to render. And we're going to come back and look at it when I'm done, and I think it will answer your question. So try not to let me forget. Well, okay, I'm going to refresh it one more time and see what happens. Nope, still there. Okay. All right. We can... yes, the W's have persisted. I got a bug report after presenting this to the undergrad, and I thought it was very principled, because in fact I was using W and M, and I was using different values for them, but you don't have to. It's an unnecessary complication, because W is like the number of entries, which doesn't have to be the same size as the number of hash values or something. It's quite confusing, so I tried to take it out, and it's still in here, so now it's actually more confusing than when I fixed it, right? Okay. Let's look at an example, and this example actually works. Nope, I'm not going to use command, I'm going to use term. Okay. What is it? It's not hot in here, so if my computer's hot, it's the computer?
Yeah.
Okay. Okay. So what's the narrative here? Probably easier to select. This all cancels out, right? Divided by m times m. Doesn't particularly matter because we're doing math form, so we can do a times x. And what we can see is that we have h 55930, 5256, and we can do an alternative h. Oh, I can't even type. Okay. You should all know that I've submitted a request for a new computer 4 years ago. Okay. We are all living in the house that we built, I think. Okay. So we can see that all of this sort of extra math flooring, presenting, dividing, and stuff, you can take that and you can just regard this simply as 5 is co-prime with 256, right? Okay. And then what is the nicety here? Well, we don't necessarily know if our value is going to go up or down at any given time. Now, this is a relatively insecure hash because most of the time we're going to see something change by the amount of 5 every time we increase the value. But in fact, if I increase this by, I'm trying to do some math in my brain, which is always dangerous. Surely this will work. Sometimes when you increase by 1, you get a smaller value, and you get a markedly smaller value. So what this means is we can also throw all of this stuff into binary. And we can see the binary representation of 98 We can see the binary representation of 103. We can see the binary representation of 253. Oops, 253. And we can see the binary representation of 2. And you'll notice these bits are getting scrambled up, all of them, at relatively high probability. Now, 5 is a very small number to be co-prime with something, right? So we're not really getting a lot of benefit there, but we can pick considerably larger prime numbers. For example, oops.
Sorry, what's co-prime?
Two numbers that do not have a common divisor. So 9 and 6 are not co-prime because they both share 3. But we can also find numbers that do have divisors but don't share a common divisor. And so we could take 15 and 16. 15 is divisible by 5 and 3. 16 is divisible by 2, 4, and 8. But they have nothing in common.
So they're considered co-prime?
Yes.
But it's not co-prime numbers, it's just a division.
It so happens that prime numbers are co-prime with everything, which makes them very useful. So I don't know what's co-prime with 256. Anything that I get by multiplying 3s and 5s together would be, because 256 is a power of 2.
So they're said to be co-prime when they do not have.
When they don't share a divisor. And co-primeness is quite useful. Now this one's too big. This is a multiple of 256 plus 1, this problem. Do we know our Mercian prime? What is 5 times 3 times 5 times 3? Okay. There we go. This is changing a lot. So we can relatively intelligently construct these things by arguing that 2 to 56 is 2 times 8. Is that right? Must not be. Did I miss a 2? Oh, that's 7, right? So one of the ways to express this co-primeness is I can express 256 as all of its numbers. And I can express whatever this number is, which is 225, right? Is that right? Yeah, it's 225, right? 5 times 3 times 5 times 3. 25 times 7. Yes, 25. So 225 and 256 are relatively close to each other, so we scramble a lot of bits each time. But they have no common factor, which means no matter how many times I add this number to that value, I'm not going to loop back to the same value. I'm going to keep coming back to slightly different places within the 256. They sort of offset a little bit each time. And so I'm sort of dancing atop the bucket with 256, and I'm going 225 across it each time. So it's quite likely I go into a new bucket every time.
Can you rotate around? Like if I did another 3 times 5, or no, there's a balance and you can't go outside.
Just has to be co-prime. So this will scramble as well. And we can debate the comparative merits. It's often useful to have smaller multiplication values because multiplication is expensive in computers.
Yeah.
So these are small multiplications. All of these things fit in a 16-bit integer.
So is it kind of the minimum amount you need?
You really want to do the minimum amount. Yeah, because it costs money. Yeah. Oh.
I'm not sure if it's starting to play, but I'm trying. So I think something is happening from the binary representation of the numbers when it's multiplied, and then when we modulo, something is happening. How should we be thinking about that multiplication, or should we be thinking about the multiplication? Is that the right frame?
Yes. The way I am thinking of multiplication right now is not strictly as multiplication, but the combination of a multiplication and also a modulo. So I multiply by one value, divide by another value, and keep the remainder.
So I'm not as confused about like the actual function itself, but more so if I'm like, because I'm guessing you want us to be thinking about the binary representation. And maybe you just answered this question and I just didn't get it, but like, if I'm thinking about like the manipulation, right, like from the macros,
Mhm.
we're thinking about each bit individually. And so I'm guessing you want us to be kind of doing that translation for what we're seeing now.
Yes, we should think of this as an arithmetic way to achieve the scrambling of bits that is similar to the bitwise operations way of scrambling bits that we did on macros. The usefulness of thinking it this way is in RSA we're going to do a lot more multiplication based, not hashing, but encryption. So I'm introducing a form of one-way hashing using modulo here. If we look at this in binary, what we should expect, and I'm going to drop back down to 225 because it's easier for me to think about. If I put 1 in here, we can also just look at the binary representation of this. All of these binary values will be 8 bits in size, right? And I'm going to claim that we're going to see these bits change at very close to 50% probability with this. It's possible I did some of my napkin math wrong when picking an example, but I think it's going to be quite close. I'm going to make a testing function to do this a little bit easier. But let's look at the binary. Bin H X 255. No, 225, 256. Okay. So let's see. That one changed and that one changed. So 2 of 4 changed. That's not, or 2 of 8 changed. That's not great. 1, 2, 3. 3 of 4 changed. That's not bad. 1, 2, 3, 4. 4 out of 4 bits changed. So this is not perfect, but it's pretty good. Okay, there's an implicit 0 here, which means this bit changed and all 3 of these changed, so 4 out of the 8 bits changed this time as well. So I'm seeing very close to 4 of the bits changing each time, but I'm never seeing, or I'm not always exactly seeing 4 bits change because that would also be too predictable. Let's do one more. 1, 2, 3 changes, 3 out of 4. So I'm thinking of this binary representation, not even necessarily as representing numbers, but representing the amount of security or distortion or protection or confusion. All of what I'm doing here is I can reverse that transaction, presumably somehow, or I can at least verify that it was generated by a 6. It would be very hard to guess that 6 will generate that successfully. And so it would be easy enough to say, well, if you want to get this output, what can you put in here instead of 6? And you can think about how hard that is to do, and it is non-trivial. And it's not that difficult either, but of course this is not the secure hashing algorithm, this is just the hashing algorithm. And is more secure than Python hash. That was a little bit too easy. Good work. Okay. I also wrote this in C. In C I wrote it with bit shifts instead of multiplies. Because it's faster. I also checked the size of things and so on. But you can just throw this into C. I'm also using unsigned instead of UNs here. I'm a little bit nervous about what's going to happen if I attempt to boot the WSL kernel on my computer right now because it just couldn't run Python and it's hot to the touch. It really is the year of Linux desktop, don't you think? Like, if I were on Mint, this would all work, right? And if I were on Arch, it would really work.
Confirmed.
Yeah, right? Yes.
Yeah.
I asked for a computer I can install Linux on, and they're like, we might have a loaner. I was like, I am not going to install a new operating system on a loaner device. You are trying to get me in so much trouble. Because then Witz is going to come and be like, hey, how do we get this off of here? And be like, I don't know, reformat the hard drive. Okay. Yeah, any of y'all ever reformat your hard drive? Yeah. I did once, and I was like, that was a lot more work than I expected. Like, there was...
I loved it. I just did it recently.
You did it? Okay.
I feel like it's, I mean, I think Jace did it recently too. I mean,
Mhm.
just hitting one key, like you're in Vim, and deleting a whole partition, that felt
Yeah.
incredible. I feel like it's so much power.
You definitely have power.
Yeah.
I have so many, like, receipts saved in my downloads folder. I don't know who put it there, because I don't remember downloading them, right? But, like, I'm the only person with access to my computer, Mr. Plus. I think what happens is, like, while I'm in character as a computer science professor, I know how to use computers, but then, like, when my guard's off and I don't know that people are watching me, I turn into, like, not a power user. Like, how do you make folders? Like, I forgot. Okay, this is the bad thing that can happen. We should always think about bad things that can happen in a cybersecurity class. And the bad thing that can happen is we have two values, x and x prime, for which when we apply our hashing function, h, we've named it, we get to the same hashing value. Why is this a bad thing? Well, because the thing we could be throwing into our hashing function could be a potentially desirable program, and we don't want someone to be able to throw a potentially undesirable program into our hashing function and get the same result. Because the usefulness of this hashing function to us is a way to form a contract with an end user. We create a piece of software, and we put it on the internet. And we compute the hash of it on the internet. And then people can download our software and verify they got the version that we tested to see if it was safe. Now, they still have to trust us, right? But now they don't have to trust anything on the way. And this notion of not having to trust people that are maintaining the backbone of the internet is useful, because at any given time, the backbone of the internet is maintained by Verizon or Elon Musk or the United States federal government or any other number of people that might have opinions at any given time, right? And for some reason, it's never maintained by public universities, right? That's never who's doing it, right? It's always private universities like MIT. Ugh. Okay. How do we avoid collisions? Well, two things. We make an intelligent choice of A, the number we're multiplying by. We select it to be co-prime. And do we write a proof it needs to be co-prime? No, but you can. Go write one if you want. It's relatively nice to see why you would want to do that, right? And using something that is prime instead of co-prime makes the proof correspondingly easier, but it is harder to find prime numbers than co-prime numbers. And so we're going to do something called a large codomain for H. What is the codomain of H? Well, H is a function that takes numbers and it goes to a subset of the numbers. You cannot get every number back out of H. Specifically, you can't get back anything bigger than m. And what this means is that if you have more than m things for which you try to hash, eventually two of them will hash to the same value. And this is very simple to do by picking a very small h. Oh, hey, it loaded. Okay.
Can you say that last bit again?
We want to have a large codomain for h, our hashing function. We achieve that by having a large value of m, which is the thing we are taking the modulo with respect to. So if we take any number modulo m, it is necessarily less than m. So we pick a very big n, and then we have a lot of numbers that can come out of h. Let's look at an example. That looks good to me. Now I'm on Linux. Wait, there. I have to type Python 3 instead of Python. And I don't need to call this h prime. Okay, h. Okay, so we can take h of 1. We can pick a number that is co-prime with all numbers. I'm going to do 17, and then we will do a small m value of 5. Okay. And we can pretty quickly get a collision here. I'm doing the birthday paradox. Do you all know what the birthday paradox is? I'm quite likely to get two numbers that are the same before I get two ones. Right. All of my numbers are going to be 5 or less. There are 5, no, they're going to be less than 5, so 0 through 4. 0, 1, 2, 3, 4, 5 possibilities, right? It is unlikely that I quickly get 2 1s. It is relatively unlikely I get 2 2s. It is relatively unlikely I get 2 3s. When you put all of those things together, you're quite likely to get 2 of one of them quite quickly. Because my first guess is going to be one of the things in 5, one of the 5. And then my second guess is either going to collide with the first guess or be a new thing. And then my third guess is either going to collide or be a new thing. So it is already quite likely I get 2 or 4 back, right? I'm either going to get 0, 1, 3, or get a collision. So I have a 40% chance of getting a collision on my third bit. Now I go up to 60%. No, it's a secure hash algorithm. We did it. I wonder what's going to happen here. Oh, okay. Yeah. And there's our first collision. Ta-da! We got it relatively slowly. And I think we got it relatively slowly because 17 is bigger than 5. So this is the bad thing that happens. And this also means that this happens if we put in comically large numbers. Wow, that thing has the exact same hash as 3. You know, a little bit too easy. So, let's think about goals here quickly, and let's think about what these things are used for. I've suggested that these hashing algorithms are used to implement the hash map object, which implements the map interface in Java, which supplanted the dictionary object in Java, which only had one implementation type. Or I can use Python dictionaries. And in that case, we're working in a non-cryptographic application. We're working in a data structures application. In a data structure, we seek only to minimize collisions. We can deal with collisions with a variety of things. If you are in a data structures class, you deal with chaining, cuckoo hashing, linear probing, multiple hashing. When you hash 2 things to the same location in your hash table, you simply deal with that somehow. It is not a security problem, it is a performance problem. Which means that if you have a highly performant hash function, it's worthwhile to deal with those consequences, right? In a cryptographic application, we want to avoid collisions completely. We want to hit collisions at probability very close to 0. SHA256 is going to have collisions at probability 1 over 2 to the 256, which is a very large number.
Yeah. So, you got a question?
I did.
Oh.
Please.
Sure. So, this was, I was implementing SHA256. I saw, right, there's all the K values, all the H values. And I think one thing that stood out at the end of it was that, I didn't have to say about this too, who came up with those values to use? Because I think that's there to avoid collision, right? And you said...
Not really. Like, the initial values are arbitrary.
Really?
You could start it with any values, yes.
Yeah.
They're not well suited to avoid collision.
What about the H values? Those are all arbitrary?
So like the H values, which are the fractional components of the square roots of the first n primes, those are choosing to be able to reproducibly be generated anywhere, right? So rather than having to say, here are 256 bits that we are avoiding getting scrambled, they tell you a way to calculate the first 256 bits. So those were optimized for reproducibility, they were not optimized for security. You can run SHA256 perfectly well, starting on all zeros.
Okay, that's pretty interesting. So then, okay, so the starting values don't actually mean that much.
Yeah, they're all meaningless. And the round values, which are the K values, the 64K values, those are also arbitrary. I think you run into problems if those are all 0. But certainly if they were all 0, 1, that would be fine.
Okay. Okay, now some follow-up questions. One, just on the co-prime thing. So co-primes are how you avoid collisions.
Mm-hmm.
Is there a simplified version of why that is, or no, it's pretty complicated mathematical thing?
I would use a combinatorial proof based on counting necklaces, which I am going to teach in a few weeks. Where is it? Yeah. I would describe it this way. And it's essentially related to distance from something. I only have an intuitive sense of this. I've never had to say it out loud before. So, if a number is co-prime with some other number, we'll say they're A and B, and we take some multiple of A, so we say NA. It is unclear if NA's remainder by B. That value should be changing with respect to if they're not co-prime, what happens? Right, if they're not co-prime, then that means when you multiply A by certain values, it increases by a partial multiple of B. I wonder if we can illustrate this by using 15 and 20. Okay.
While we're here, that was kind of the question. I was wondering about the distribution of numbers with co-primes.
Yeah, let's look at 15 and 20, and I think this will be easier to demonstrate with an example than me try to explain it. Okay, so these numbers are not co-prime. They are both divisible by 5, but they are different numbers, and they are quite different, right? They're as different as any two numbers which are not co-prime, right? Or perhaps they both have 2 digits. If I put 1 in here, I get 5. And why is that? Because I multiply 1 times 20 and then take the remainder with respect to 15. If I put 2 in here, I'm going to get 10. And what we realize at this time is that everything that comes out of this function will be a multiple of 5. It will be a multiple of the common divisor. And since the common divisor here is 5 instead of 1, that means we will be using many fewer of the possible values that are less than 15. So this is equivalently secure to the hash function for 3 because it produces the same number of unique hashing values. So collisions are dramatically more likely if you do not have coprime values, and they are as many times more likely as the greatest common denominator.
Gotcha. So, what did you?
That's all.
So then, just to add on to that, right? So this is producing 5 and 10, but in SHA, it's the same, character length of output.
Mm-hmm.
Would that be padded with zeros? Would it be 5, 0, 1, 0, or how would that affect this animation?
I'm regarding the outputs as being exactly the same level of precision as the modular value. And I'm actually regarding these as having fractional bit precision. So that is, I consider this to have, this is a hash algorithm of size log base 2 of 15. And the reason for that is the number of discrete possible values or the number of discrete possible bits that could be stored. When I say fractional values, what does that mean? Well, it is not as if we can use a fractional number of bits to store something. And the classic example I think of is Latin characters, of which there are 26. But you do not need 5 bits, which is 2 to the 32, to store 5 letters, because you can store pairs of letters.
Mm-hmm.
Which means that if I give you 1,000,000 letters, you do not need 5 bits per letter. What you need is log base 2 of 26 bits per letter. And then you can store strings of letters with unique bits. So SHA256 happens to be not just an integer number of bits, but a power of 2 number of bits, and in fact a power of 2 of a power of 2 of a power of 2 number of bits, right? It is an extremely well-behaved size. And it is an extremely well-behaved size so that the algorithm is can possibly be implemented by humans and also can be implemented by circuitry, which prefers there to be powers of 2 of things, right? But there is no law that says we can't implement SHA, some large prime number. I don't know if 127 is prime. Probably not. Is it? Should be divisible by 8. I'm not going to try and do that in my head. That was bad. That was a mistake. You could do SHA 127. It would just be painful, right?
Gotcha. Okay, so then, I lost it. There's something else on top of this. Oh, it was, yeah, that, okay, so when we're doing the homework, we're given, you know, the same set of constants, the same set of h values. So when we comparison, it's the same hash, right? My question is, in practice, does everyone implement their own version where they change the constants and change the h values, or they always use?
Yeah, it's not SHA256 with different values. And we want SHA256 to be reproducible because the goal of it is to not produce things that are unpredictable with respect to input, but predictable when controlling for input.
Okay.
So
gotcha.
any two independent actors, if they are aware of SHA256 and they have some bits which they wish to verify, even if they don't have the library, if they know the algorithm, they can separately implement the algorithm. My takeaway from the homework assignment was I can just say, I know this SHA256 sub-utility exists. I have not seen the source code. I do not know what H values it uses. But I can look at the documentation of SHA256 and write my own code. And I got it to do the same values. This is interesting, right? This means we have a way of expressing with arbitrary precision algorithms in a way other than code, right? Which is a very significant result of SHA256, that people were able to write this thing down without using a programming language and still communicate it between humans.
Gotcha.
And the humans can turn it into code, right?
Gotcha. Yeah.
And I think it is a marginally academically interesting exercise because most of what you do in Python and JavaScript, if you do this, is wish you were writing C. But you can, in fact, write it in Python and get the same value. And you can write extremely cursed Python, right? So you can do it in a single line list comprehension if you want. And yeah, that looks quite different than the C code, but it's logically identical in this very interesting way.
I think my overall question was, you know, if I, right, like you're saying, they're always use the same values that you can compare. But, you know, I could just take the base of that SHA256. If I just were to change those values so they're arbitrary, I could have my own, you know, personal version of SHA where I can verify against anything that I use in those values. But no one else could. I don't have a use case for it, but that's something that's possible.
Yes.
Okay.
And it's worth noting that that is also logically equivalent to adding a 512 character bit prefix to everything you distribute.
Okay.
Because the initial hash values, they are displaced in all later blocks by whatever the hash of the previous block was, right? So we're essentially just imagining we have a phantom zeroth block that happens to produce those hashes. So there are in fact two ways to do that, right? You can manipulate the H values. The K values are different, right? But the H values can just be manipulated with prefixes.
Gotcha. Okay. This is my last question. It goes back to hashing, coding. So if everything produces the same hash, right? I was thinking in terms of passwords. You know, if I saw a bunch of passwords, let's say I entered ham as a password, it would have the same hash output for me and any other user.
Yes.
And you know, I could just see that, okay, I don't know what the password is, but I see everything is coming out to the same hash, the same values. So I looked into that, and they talked about a solution called salting, which, you know, goes back to salting your hash browns. And so my question is, for a salt, which they said is, you know, randomly generated and attached to anything and then hashed, is that stored somewhere? Is that randomly generated every time, or how secure is that?
Yeah, I didn't ever look into salting that much. It's academically interesting. It's also used in hash maps. And I'm sure there's like very specific professional standards on how you're supposed to handle salts. I would assume that if I were operating a password management service, I would generate a salt based on the most unique things that I think are unlikely to be discovered about an individual given user. So I expect a large number of my users to use password as their password. And I personally find this inoffensive. Like, I think people can make their own decisions about their security, right? But I don't want it to be obvious from the inevitable data breach when AWS East is not actually as secure as they claimed they were in my contract. And so I want all of those passwords to hash to a different thing. And so a very easy thing to do is just add the username and the password and then hash that. And that's a little bit of a trouble if someone like changes their username. So it's like, are there any immutable characteristics of the person that made this? Like, do I store, you know, the MAC address of something that comes in? And there's going to be a variety of industry best practices to do that, and I don't know what they are. You can even just use unique user ID. So
Gotcha.
we know we can just add 1 to these things anytime. So if you are the 4th user on the site, I simply add 4 to your password. You say, oh, you can't add 4 to password. It's like, yes, I can do whatever I want. They're bits, right? I can multiply it by 4. I can put it in Python hash after I multiply it by 4. I can do all of these things before I throw it in SHA256, right? And if it comes out of SHA256, it's secure. So I can do arbitrarily insecure things to it before that, right? As long as I can remember what they are. And so I think naively that's how I would do that, and then I would say with the appropriate caveats that is certainly insecure for a reason I'm not thinking of.
Gotcha. Cool.
Were there hands over here? Cool. Are the vibes good? Do we know what time the pizza place closes? I've had 2 donuts and air today.
9:30.
Okay, we're fine. Cool. This is called combinatorics. Look, I thought it was going to be a CS class. I legitimately did not think there was any number theory in this class until I started doing my slides, and I was like, oh, I don't know how to explain what coprime is, right? And I was like, guess we'll do GCDs. And I was like, what's a GCD? I was like, how do you decide? And this is, so I have not gone into this detail, but there's like, well, we have a way of determining which numbers are larger than other ones. And it's like, no, I haven't done that. I stopped there, right? But like, in fact, you can see how many bits they take to hold. And like, okay. Okay. This is the definition of codomain. Blah, blah, blah. You've seen that before. This is what codomains look like. Oh, yeah, that's fine. Yeah, it's just review. You should always, my impression is, versus when I was learning all of this stuff, you should never, under any circumstances, look at a reference other than Wikipedia for formal mathematics. It seems dramatically better than the textbooks. And I have some textbooks I like a lot, and they are definitely worse. I really prefer the term set of destination because I think it's self-explanatory. A function can return some number of values. Or perhaps there's not a number. Perhaps I can't have. So square root does not return a number of values, right? But everything returned by square root is positive. So it is a subset of some other set. Right? And so this is the set of things for which f can return that thing given any arbitrary input. And so a hashing function, we would expect, at least the ones I was demonstrating using the coprime mod technique, which is the most naive form of hash algorithm. Their set of destination is the integers mod m. Working out what codomains are is pretty interesting, right? So the codomain of addition over the natural numbers is also the natural numbers, but the codomain of subtraction over the natural numbers is the integers, because we can generate negative numbers by subtracting positive numbers from positive numbers, which is extremely annoying if you're a computer scientist, right? Because I really don't want there to be negative numbers. So codomains are fun. And so, yeah, the integers were constructed with the codomain. The imaginaries are constructed with the codomain. What is the square root of minus 1? Ah, no problem. It's the codomain of the square root is the complex numbers. This picture is pretty good. If you really want more on those, which I did not expect, but I do have very good slides on this. It's probably diagonalization. Right, yeah, so we have surjective and injective and bijective functions. You can look at all of this stuff. Here we go. So this is the codomain. This is the domain. And there's different types of functions that map between things differently. I forgot I can just click on a place. So here's our different families of functions that are defined by their codomains. They're sets of destination, also they're sets of inputs.
Does SHA use a specific one of these?
SHA is surjective because it maps everything into a small set. But it can map multiple things into a set, but it maps 2 things into any one thing at low probability. And the probability is 1/2 to the 256. And how big is 2 to the 256? (256) is roughly 25 times 10. 2 to the 10th is roughly 1,000, so it's roughly 1,000 25 times, so that is a 1 followed by 75 zeros. Some large number of billions, right? A billion to the 9th, something like that. Large number, right? But not impossibly large, right? So you would expect Google, Amazon, Microsoft, and the United States federal government to be able to reverse one of these in a couple seconds, and no one else to be able to do it ever, basically. So I'm assuming they have several billions of computers that can do millions of operations per second. Visualize. What? Okay. Okay. So that is meant to give us a theoretical foundation for thinking about hashing algorithms. What are the big takeaways from this? We can take anything and get back a thing of a fixed size. And we cannot predict what the thing of that fixed size will be, no matter what I do to what I put in the beginning. It is just like hash browns. No matter how many potatoes I start with, I always get enough that I want to eat them. And I never know what they're going to look like. And if someone puts some cyanide in it, it will taste very, very different. Right? Do you know MCR? Are they cyanide and happiness? Anyways, MCR is going to Seattle and not going to Portland. Do they not know about us? We're like at least a top 5 emo city in the Pacific Northwest, right? It's got to be us, Eugene, Spokane, Bellingham, Tacoma, right? Okay. I just bought some tickets to an emo show because I decided I like being sad. Okay. SHA1 is not secure. I don't know why. I didn't look into it. I have told the undergrads at many points in time that I like SHA256 a lot more than other hashing algorithms and cryptographic algorithms. And I like it for this very specific reason, which is that this thing is not even remotely mathematical. I have gone through great efforts to describe it mathematically, and in fact you can do that, but this was absolutely 100% made by electrical engineers. And you can tell that because it has bitwise operations in it, which every single mathematician hates. Because you can, in fact, express them mathematically, and why would you do that, right? Because you would express a bitwise numerical operation over a set of values that range from 0 to 1. And no mathematician has ever wanted to do that, ever, right? They don't really work with mathematical objects of that shape. But electrical engineers work with transistors all day, which are either 0 or 1. So they love combining zeros and ones, and they made an entire number system out of it. It's called uint64t. I love SHA because it feels like one of the few things that's actually computer science in the sense that the physics is leaking in. And I love it when the physics is there because it means we're doing something that we shouldn't just be doing with mathematical proofs. We're going to do RSA, which I also love. Never once while working on RSA have I felt like I've been doing something that a computer should do, right? Because it's all divisions and prime factorization. And computers can't do that. They're bad at it. That's the entire premise, right? Computers are very good at SHA256, and that's why it's cool, because computers are cool. Computer scientists are cool. Yeah! Okay, all right, okay. It is unlikely in the next 2 or 3 decades that weaknesses in SHA2 are discovered. The eventual weaknesses will be related to things we did not anticipate, such as they produce unexpectedly predictable electromagnetic signals under certain circumstances. They produce heat in overly specific patterns. The first rounds of attacks on other cryptographic algorithms have left SHA completely unscathed, because many of the cryptographic algorithms that are falling out of favor now, the way they are insecure is that you can guess a lot of information about what is being encrypted based on how long it takes to encrypt it. You already know how long everything is with SHA256, and it runs the exact same number of operations given the same input size, right? So if I put 10 gigabytes into SHA256, I can make no conclusions about how many zeros or ones are in those gigabytes based on how long it takes the algorithm to run. That's pretty cool. I think that the most sophisticated attacks on SHA2 look both unrealistic and uninteresting to me. They make assumptions about the level of control someone's going to have over something they care about a lot that seem unrealistic. Now, of course, the first time someone beats SHA256, which could happen someday, right? It will be in an extremely contrived circumstance, right? But it will reveal weaknesses in the algorithm nevertheless, right? So it is interesting to see how people are attacking it, but I looked into how people are attacking it, and it made me feel a lot better, which is not always what happens. Separately, and this is not true for every hashing algorithm, SHA3 is ready to go and also has no known weaknesses, right? This is unheard of. When RSA started taking heat from the side channel problem that Bart Massey and the Rust people are trying to solve, it was a disaster. The future of what RSA does, which is public key encryption, is elliptic curve cryptography, and was not even vaguely ready to go. Many of the algorithms that are being deployed right now are not as provably as secure as I would like them to be. Right? We have assumptions that they are secure. The proofs have not gone through. We need a lot of PhD mathematicians to look at this stuff for a long time. I don't consider them ready. I consider that to be a wildly insecure area right now. No one, to my knowledge, feels that way about SHA. This is the gold standard. It would be interesting to see if we could get things this robust in other applications. Now, the SHA application is a little bit too easy. You're just checking if things are correct. You're not trying to keep secrets, right? So it's unsurprising we can do much better. But I am very impressed with SHA, and I really like working with it for that reason. There are 6 functions in the family, and that does not matter at all. To my knowledge, there exists no implementation of the secure hashing algorithm that implements all of these correctly. The 2 most common are SHA256 and 512. To my knowledge, there is no implementation of both of them that is completely correct. The thing people always do wrong is they assume that they are working on bytes instead of bits. That's a very good assumption to make because I don't know how you would get a non-byte amount of information. But in fact, the algorithm does not say you are allowed to assume that there are underlying bytes. So that means people have not actually implemented the algorithm. They've implemented the subset of the algorithm that assumes that all of your inputs have a multiple of 8 bits of information. When is this wrong? There does exist this thing called base 64 encoding. 64 is 6 bits. 6 and 8 have a differing factor of 3. And so that means that sometimes I can have a non-divisible by 8 amount of information. Has this ever been a problem for anyone? Of course not. You pad by 0. No one cares, right? What is this thing mostly used for? To me, well, I mean, it's used for everything in the universe, right? Bitcoin, that's why we're doing it in this class. This is used to sign transactions. Bitcoin mining is computing SHA hashes very fast. And doing this at all is fun, and doing it fast is really fun. I fell down the rabbit hole of trying to write GPU code that computes SHA256, and that is a very fun rabbit hole to fall down. You can probably just do that for the rest of your life if you want, right? I have heard that not everyone loves writing CUDA C++, and I'm kind of skeptical, because every time I'm writing it, I'm like, wow, this is awesome, maybe I do like C++, right? Which is not something I say lightly. So, what is it used for? It's used for digital signatures. It's used to verify the integrity, the correctness of a downloaded file, or perhaps an email. It's used to validate certificates, so I can say, hey, we made this agreement or something, and then I have this hash that shows I didn't tamper with it, right? I think in real life, people like sign contracts. That's not really good enough for computers, right? They don't do that. Right? File integrity verification, so something that would be nice to do, right? From time to time, I travel, perhaps internationally. Perhaps my laptop is inspected. Perhaps I want to verify that while it is being inspected by someone I don't trust, that no underlying changes are made to the file system. I simply compute the hash of my entire file system, which is no problem, right? There's only about a terabyte on there. Right? This should take moments, right? So I hash my file system, and then I roll back until I get a hash that I look familiar with. And I'm like, oh, maybe I don't know it was tampered with, right? But I can get rid of the tampering. That's an application that makes me feel a lot better, because a lot of these things are network applications. They're like, I already don't trust anyone on the internet, so like being able to verify that they are, like, when Ubuntu says, I computed this hash, it's like I kind of already don't trust Ubuntu, right? I'm like already running that stuff sandboxed. But I really like to be able to verify the intensity, or the integrity of my own physical hardware. I should point out, because I've pitched the Rust class, why are we doing SHA256 in this class? It is easier than SHA512 in the sense there is less typing. It is exactly as intellectually complex. I view there as being no difference in intellectual complexity. SHA256 is used in Bitcoin. In the Rust class, you do SHA512 because it's used in ECDSA, which is the thing you do instead of RSA, which is the new technology that I'm not sure about, but is extremely cool. But is it as cool as RSA? I don't think so. That's why I'm teaching RSA this year. Okay. Every once in a while, a student comes up to me and says, why don't you just teach a class where we go around and implement all of the cryptographic algorithms? That seems like a great way to learn them. And I say, I do think you should do that. But not everyone says this. And in fact, the general consensus in academia is that I should not give you a homework assignment to write SHA256. And the reason for that is people are concerned you will think you can write your own cryptographic algorithms and they will be secure. That is untrue. It is very untrue. It is staggeringly untrue. The degree to which it is untrue was shocking and horrifying to me. And so, because I'm breaking the law and telling you to implement your own secure algorithms, you must pledge to me verbally to never use them. So raise your favorite hand and repeat after me. I will never use any code I wrote in this class for anything. I am only doing this for fun. This class is fun. Thank you. Okay. So, every once in a while, someone notices that SHA256 has a maximum size, and so I'm going to point this out to them. And it is in fact true that that size is non-infinite. It is specifically 2 to the 64 minus 1 bits. That's a very large number, equal to 17 million terabytes. What does this mean? You cannot use this to verify the integrity of the data center. You would have to do a little trick I call verifying 17 million terabytes at a time, and then taking a hash of all those hashes. So that is a tree. And in that case, you would have to have a tree of depth 2 to verifiably hash all of the information that has ever been collected in human history. Which that seems like a pretty okay deal for me. I don't think that'd be too hard. This idea of hashing hashes is a little thing called a Merkle tree. It is how transactions are stored in Bitcoin, which is super cool, and we will do after break because there's no way to do it memory safe, and we're doing memory safety until break. Okay, and we will come back to this after dinner. Does anyone have 3 to 5 minutes of questions? I shouldn't have asked that after saying the alternative was dinner. Okay, let's eat. Is anyone leaving because I can't get back in? Hero, icon, legend. Okay. Thank you. I will screw that.
Computer vision. Oh, it was studies of factors. Data science and Python. And one of and then data engineering computer and sales. Yes. Like their next campus task. Computer vision. It's exactly what it sounds like. It's not I've lost my human vision. But the computer can see now. Yeah, I'm doing machines in my head. So like the computer vision. Do you guys have this name?
I'm just thinking, I don't know if I agree.
Oh, it's not fair.
If there's only 2 of them.
That's cute. I think computer vision will be like this.
I would want to take advanced data engineering.
I would too, but it's not. Yeah. Well, I mean, the Python and data science also supposed to be in sales, I think, or is there one here? Because I know there's a third class here. I just don't remember what it is.
On the survey,
Yeah.
I thought I only saw three. One
Yeah.
was saying tech computer choice.
Right. Oh, I don't mind either. Or even petitioning for the data engineering too to be taught here. Yeah.
I was thinking I was going to see who's interested in this.
Yeah.
And if not, I'm thinking I'll speak to.
Sending one of those like little delivery classes.
Oh, so I was going to do 2 classes, one in the next semester.
Yeah.
I'd rather not take a third class regularly than like instead.
Oh, yeah. That's true, it is. My thing is that if I do that, then I mean, I'm pretty sure I just want to graduate because I don't want to draw this out by taking another class because it doesn't look like I'm going to have a job for the summer, so there's no point in not taking that unless they get into the diploma so I can say I have a master's in computer science on my resume.
I mean, they're fine for yourself.
Okay.
But this is not an exception.
Right, yeah. I mean, my thinking was I will continue taking a full-time load unless I get a job, in which case I can figure out what I just work for a schedule to have like free time to get everything done. But honestly, I could probably handle it. It's just a job I would get. That's entirely theoretical because someone's still in fights. So
I recently made a intern resume. I'm just gonna cross.
basically with like removing a bunch of your experience. So
Yeah, and it goes well.
Okay. Okay, gotcha. Yeah. Stupid. I'm gonna get some good reviews for us. Oh, not that order.
That's good. I don't know what's gonna happen.
Yeah.
Yeah.
The lunch break, the dinner break is the same size, no matter what I can hear.
Because like dinner and bathroom is gonna go around, so they'll never tell you.
The lunch
They
break.
should never call.
Oh, yeah. We can have like a no closed door policy at our house because our cat just goes in town. And the door is closed. He's like, what's going on? Like, I'll like let him in the closet. He'll come, I'll close the door, and he'll be like, let me back in. He just has to have the door open. So we like never close any of the doors like us. And like the ones we do keep closed, like to the attic where there's like unfinished insulation and shit. Like he just demands every day to get let in there. Like occasionally let it in, but for like the basement, it's not even the he doesn't even want to go down there. He just wants the ability to go down there. You know, he's got FOMO. Yeah. Invest cat.
Not upside down now.
That's good. What else do you do?
It was to be
And actually, you know, we are like,
It's like time was 108 or something, a bunch of letters, or a hanging zero.
Any thoughts on her
yeah,
plans for the summer? What are you just going to go here?
it's like it's to be able to know which parts of his words you like, or their words you need to. Yeah.
Yes.
Because I know you're saying interesting things, it's fantastic, but I'm also trying to learn SHA256.
Yes, all of the things.
Yeah. But I just asked ChatGPT to Eli by it for me.
Yeah.
Oh, so the crazy is maybe not.
Explain like the five.
Yeah.
And then I just ask it to get more complex with parts that I don't understand.
Right. Oh, because the
So
whole
I'm
trick
like,
might.
first
So
we're
then that
going
would like you
to
might as well try to control your
but I'm
limits.
not sure if we're going to learn about this.
Yeah.
That's fair. Super smart about actually work with ChatGPT.
Some people like look at my usage and they're like,
Yeah.
it's bad.
No, I don't need desktop audio. We need this thing. Okay. This was the free bonus lecture. And this lecture I split over multiple days. And you can use libgmp instead if you need to. So we can spend as much time on SHA256 as we want, and then we'll start finite and big num. Format is for next week. Yeah, we're all good. Cool. I think this is where we left off, right? How? Is that? Okay. After all of that, I'm going to still be eating and talking at the same time. The whole thing I tried to avoid by waiting until now to eat. I haven't had my electrolyte powder yet today. My calves were cramping earlier. I'm in shambles. Right? This is the weakest I've ever been. If you want to challenge me to a fight, now is the time. I'll be a complete pushover compared to my relatively weak baseline.
What electrolyte powder do you use?
Well, I think love comes in all shapes and sizes, so I use Gatorade, Noon, and Scratch, and LMNT. Element. Not usually. So I do Element post-workout, Gatorade as a meal replacer, because I can't eat solid food before I run. I use Scratch when I'm trying to get along with my family, because that's what they like. And then I use Noon when I'm non-athletic but want to feel better. So they each have a place in the symphony of God's creation. Yeah, never worked for me. I don't know. I will try any electrolyte powder that is recommended to me. But yeah, I never had good luck with liquid IV, but I will retry it if you want me to. Do you recommend?
You don't have to.
Does it work for you?
It works for me.
Okay. Do you use pre or post workout? Post. Okay. Thanks. I used it pre, so I'll try the other thing.
Or you want to be
Yeah, but that's always right. Hydration check. Hydration check. Okay. So you all know what the fractional parts of the first, the fractional parts of the square roots of the first primes are, right? Okay, no problem. I'll show you real quick. Fortunately, my computer is an absolute beast and can definitely handle this task. What is going on there? Okay. Why am I not in Linux? I was in Linux earlier. Okay. So, what's an example of some primes? Well, we've got, I'm not going to write a prime generator. That seems a little bit too annoying. You got 2, you got 3, you got 5, 7, yes, but not 9. 11, is 13 prime? 17. Is that 8? No, that's 7.
127 is
I was pretty sure it was prime, but you don't want to be doing prime factorizations live, right? So thank you though. I would have just assumed it's not and never checked. Been the professor's wrong. Okay. So how do you find the fractional component of a prime? And here, let's do these side by side. Where did the side go? Oh, it's full screen, so Windows doesn't know it's a window. I never thought that one of my biggest frustrations with Windows in 2025 would be that it doesn't handle Windows well. That's what it just did. I had a full screen thing I was trying to turn half screen, and it didn't recognize it as a window because it was a full screen app. You had one job, it's in the name. Okay, so we're going for this value, right? And so the way we do that is we're going to calculate a square root. I'm going to just store that in something called S. Okay. This is 1.414, which we're all familiar with as the square root of 2, right? And 2 is a prime. So how do we get the fractional component of that? Well, not too bad. We take S mod 1, and then we have just the fractional component, right? Now, that thing is supposed to be 32 bits, which I don't think I say anywhere on that slide, but it's easy enough to verify, because this is 1 byte, because it is 2 hexadecimal digits. Each hexadecimal digit represents 4 bits, so 2 hexadecimal digits represent 8 bits. There are 4 such pairs of hexadecimal digits for a total of 32 bits. Easy. So what that means is that I'm going to find a number that is essentially an integer between 0 and 2 to the 32nd. So I'll simply multiply this by 2 to the 32nd. Now, because I'm a C programmer, I'm going to do an extremely obnoxious thing where I'm not going to use the exponentiation operator. I'm going to use the bit shift operator because bits are cooler than numbers, right? So I'm going to take 1 and I'm going to, nope, I typed 2 and said 1. We'll shift that 32 times. Okay. It's about that much. And let's verify that this is what we think it is. Yeah, it looks right to me. Okay. Doesn't that look like 2 to the 32nd? And how can you verify? No, we can do it without a computer. Okay, right, so this is going to be fun. Is everyone having fun? Are you ready to have fun? Okay, I need us to lock in. Okay, that's a 4. The most significant digit is a 4. 4 is 2 squared. That's the 2 here. Then this thing is a 1 followed by 1, 2, 3, 2, 2, 3, 3, 2, 3. 3 sets of 3 zeros. A 1 followed by 3 zeros is about 2 to the 10th. So that's the 2 to the 30th. So this is 2 to the 30th times 2 squared, or it is 2 to the 10th times 2 to the 10th times 2 to the 10th times 2 squared, which is 1,000 times 1,000 times 1,000 times 4. That's what this is, 4 billion. Let's convert this to hex. What? Float objects cannot be interpreted as an integer? Okay, no problem. And there's the answer. It's the fractional component of the first times. Get rid of the integer components, or well, you do a square root, you get rid of the integer components. I just do a bit shift. It doesn't really make sense to do bit shifts with non-integers, so it's formulated as a multiplication. I tried very, very hard to do this without using floating point numbers, and I still have not done it successfully. Several points in my life, I have set out to write my own numerical library that allows me to have non-integer numbers in various ways. One time for complex values. I tried to do it for this assignment. It's just a little bit too hard to think about because you have to keep track of how far things are away from 0 and how big things are relative to each other at the same time, and it's a little bit too two-dimensional for me to figure out. And then you always want to do things like squaring, which is actually way harder than multiplication for these like strange reasons that you like have to not get confused. Let's check 3. We take 3, we take its square root, we take it mod 1, we multiply that by what? 1 shifted 32 times. Let's throw that in parens. I'm sure the bit shift operation has the same precedence as exponentiation, and it has higher precedence than this multiplication, but I don't need to check. I'm going to convert this to an integer. And when I'm done converting it to an integer, I'm going to print it as a hex value. And I'm really wishing I had Vim movement right now. Not sure it looks right to me. BB679085. I was 100% sure the first time I did this I'd have rounding errors. I don't. So the intuitively obvious way to me to do this immediately is the exact same way everyone else did it. When I say I think one of the benefits of SHA256 is you can just say to anyone who's like, I don't know, relatively comfortable enough with writing code to follow an SHA256 manual, which is not like a normal person, but also not like a world-leading genius or something, right? Like normal people with training can do this. If you say the fractional parts of the square roots of the first primes, in fact, literally the first thing I tried ever was the exact right answer. I'll put it in Discord. Okay, when I open Discord, my computer's going to crash, isn't it? I really need to switch to Nix OS. That's probably the one I should use. I think that's the most pedantic one. I was thinking I might get really into FreeBSD. Any FreeBSD users in here? As soon as I get you all into Linux, I'm going to start making fun of Linux users for not using FreeBSD, but it takes stages, right? It's important to always remember. Yeah. It's like, you use operating systems someone else wrote, you know.
This is when we need that ternary virtual machine.
Can you explain kernels to me in terms of platform?
Right. So, no. I was pretty far through an operating systems class when I realized I didn't know it was called a kernel. And I think I asked, and then the professor didn't know either. Obviously, it's like the beginning of something, like a seed, but then like, why isn't it called the seed, right? Okay, we're pre-processing. What does pre-processing mean to me? It means initializing the values of variables. Here are either 1 or 8 such variables. Why do I say 1 or 8? I can view this as a single variable that is an array of length 8 of 32-bit values. And I do say values. These things are not integers. They're just bits. This is just a way of writing down bits in text. I could write this in base 64. I could write it in base 10. They're just bits. I could write it in binary. And this is exactly 256 such bits. And this is the 256 such bits from the name. This is the hash of a string of length 0. That might be false. The other values that I'm going to, or the other variables that I'm going to initialize their value to is I have the 256-bit thing, which is the hash, and then I have the 500-bit, 12-bit thing, which is the message, or M. The input M is padded to a length that is a multiple of 512. This algorithm is ludicrously, comically, hilariously easier to implement if you assume everything is exactly a multiple of 512 bits. So they just made everything a multiple of 512 bits. What a genius move. Stop trying to deal with things that are hard, do things that are easy instead. In order to make things exactly 512, they had to have a way of making sure it was clear that everything was going to be 512 bits. And so they passed a law, and that law says that if the message is L bits long, you find the smallest non-negative k. What's k? K is how long the thing we're going to hash is. It does not have to be the same length as the message. We're going to add some junk to the end to make everything work. So I'm going to find smallest non-negative k such that k plus L plus 65 is equivalent to 0 mod 12. So if the message length is within 65 of a 512-bit variable, we're going to add an additional chunk. We're going to spill over into the next chunk. And there's going to be a ton of zeros. There's not going to be a lot of information in that last chunk, and it is going to matter to us not at all.
Isn't it 64?
No, it's 65. There's a 64-bit integer, and then there's a 1.
Gotcha.
Yeah, I mean, like, cosmologically, it doesn't matter.
No, I mean, that makes sense. The 1 plus the 64.
It is very rarely not expressed as 1 plus k plus L plus 64, and I was unable to tolerate that. Because, in fact, it is L plus 1 plus k plus 64 in that order. Because L is the message length, then there's a 1. It is 1 bit in length.
Mm-hmm.
Then there is whatever the k padding amount is, and then there is the 64-bit integer. So yes, it is exactly 65. Okay, so I give you 256 bits. No problem. You take those 256 bits, you put a 1 at the end. Then you put a bunch of zeros. And then you put the binary representation of 256 right at the tail end of the 512, and that's the 512-bit chunk that you hash. You will always hash things at 512 bits. It is so nice to know you're always getting exactly 512 bits. So this is a nicety. This is very similar to the notion of like initializing your NumPy array or calling a constructor on your object. This stuff kind of predates objects. It is way easier to write a function that knows exactly how many bits it's being handed, which is exactly 768.
So we saw the fractional slurs, and somehow those are equivalent to 256 bits. Didn't quite catch that. And we have 512 bits. And there's some relation between the 256 bits and the 512. Is the 256, is it the bucket? Or what we're trying to store the 512 in? Because those are the chunks.
We're going to create a function. It accepts 2 inputs and returns 1 output. One of the inputs is a 256-bit hash, which has an initial value, which are the H values, and those are defined by the spec. The 512 bits is the thing we are hashing. It is going to produce as output a hash. Now, if we have more than 512 bits, we feed the hash from the first chunk back into the beginning along with the second chunk. So it's recursive in that manner. Yeah, I think that's all. Is that okay? The buckets, to me, correspond to all of the possible values of the 256 bits, of which there are many. Okay, so you have your, for example, 513 bits, which narrowly doesn't fit in your 512-bit chunk, and you're like, if it'd been a little bit less, it would have fit, but quite a bit less, actually, because you still need the padding bits. Say, okay, after my 513th bit, the next bit is forcibly a 1. And you say immediately, I should only be messing with bits in multiple of 8. No problem. So after your 520th bit, the 521st bit is a 1. And then the next many bits are 0. Think about this for a moment. If I think of these in terms of bytes, that means I am putting a 1 immediately at the end of 520 bits, which is 520 divided by 8, which is 65 bytes. Which means I have a 1 immediately at the end of 65 bytes, which means it is not in the 1's place. That is in the 128's place. So one way to think of this is the 521st byte will have the numerical value 128. Right? Is that right? Did I do that wrong? I'm making endianness assumptions here.
I think so.
In my solution code, I hard-coded 128.
I think it's 128.
I think that, yeah. And 128 is 0x80 hexadecimal, which perhaps makes more sense, because an 8 is a 1 followed by 3 zeros, and an 80 is a 1 followed by 7 zeros. And that is the byte that we put at the end of our SHA hash. A lot of people always want to put 1 there, and then the hash explodes. No, the standard says you have to put it as soon as the data ends. And we are not thinking about this in terms of numbers. So we do not put a 1 there. We put a 1 in a certain position. And we're going to put the 1 in the most significant position, which means it will represent the numerical value 128. It looks like this. Okay. Then we're going to have 64 bits. What is 64 bits? It is the 64-bit representation of L. Now, many of the bits of L are going to also be zeros. Probably most of them. If we have, for example, 10 gigabytes. A gigabyte is 1,000 megabytes. A megabyte is 1,000,000 bytes. So that is 1,000,000,000 bytes. 10 of those is 10 billion. And that's 2 to the 35th, which is much, much smaller than 2 to the 64th. Right? So that means half of those bits will be 0 if you hash something that is of size 10 gigabytes. And if you hash of something of size 10 gigabytes, you're going to be there for a while, right? I think I hashed Pride and Prejudice almost instantly, but that's only a couple kilobytes, right? That's not that big, right? It's 100 pages. There's several hundred characters per page. It's just not that large, right? It seems to me like you can hash an operating system without noticing you're doing it. So it's pretty fast. I didn't really find a particularly graceful way to write this in Python because I don't like doing bit manipulation in Python. So I actually just did it with strings. So if you think of these in terms of strings instead of bits, maybe it's a little bit easier to work with. But given some length, we can compute a k value by comparing it with 512, 65, and some other fixed values. Given that k value, we can compute the size of the pad if we also know the length value. And so on something that is the size of hello there, I am a message repeated 15 times. That will be our padding value. But that padding value, importantly, is a string. That is not a properly formatted binary value. Yeah, you can do this in arithmetic if you want, and it is so unclear it was not worth showing it to you. And the reason it's unclear is it is exceedingly unnatural to say, I want a 1 at this position in a binary number using arithmetic. We don't use arithmetic to do that. We use bit shifts. Right? And yes, I can formulate a bit shift with arithmetic.
Is there a library in Python that lets you tap into the bitwise part of C?
Probably. I think there's a bit manip library. I don't know if there's others.
Gotcha.
My experience was I just switched to C. But yeah, you can do all this stuff in Python if you need to. I suspect the most useful time to do that is if you're running a Flask or Django server. It's easy to imagine there's times when you're doing things on a web server where you want to send out fixed formulations of bits. And the easiest way to specify them is to say which bits you want to be set.
I just meant for your example, I was curious if it was possible to just implement some library that lets you use the bitwise shift operators.
Yeah, there should be very good ones for Django. There should also be very good ones for, you notice in this class I use Python pretty heavily for just testing that C code works. So you can do that with C types and things like that, right? The question is always like, how much of the superficiality of Python do you strip off to get down to like, I mean, it is just a C front end, right? And so like, when do you switch back to C? And you don't do it if you're using Django, right? But if you're just writing scripts, you probably do. I think it's called bit manip. Let's try. Or maybe it's called bit manipulation. There it is. I use C types a lot. Oh, this is just all just describing built-ins. You probably want bit arrays then. It's probably this thing. Something that is odd about these, that I'm going to speculate is true, but I don't know is true for sure. We're almost certainly all using CPython, and a bunch of this stuff just doesn't work in PyPy, which is the Python JIT, and none of it works in Pyodide, which I use from time to time, which is the inscripting browser-based Python. But there's like lots of reasons to use PyPy and Pyodide like in real life. Like if you're running anything that's ever going to run on a website, you should probably just transpile into WASM, which is the WebAssembly, and just like run it in a browser. And what really surprised me on the SHA256 homework, I did this JavaScript implementation, and never in my life would have occurred to me if we did that to run amicably in a browser. Because my experience is every time I try to get something into a browser, I pass through to a C backend, which doesn't run inside a browser. So whoever wrote that had this innovation I didn't see where it's like, oh, of course you can get all of this stuff to work the way you would expect in JavaScript. It's just like I never wanted to do that enough to get it to work. So when you're doing stuff like this, it can get really weird really fast if you're doing the thing where you're running in any sort of non-standard dev environment, and usually that shouldn't matter, right? Like Pyodide is good at most things. You can run the entire Python data stack inside a browser, and it's fine. And you can't do a single one of these things in a browser. A fun thing to do is to, this is unrelated, go to the pyodide jQuery kernel. You've all seen this, right? I pull this up from time to time. It's a fun example of stuff. And you can tell it's running in my browser because it's slow. That's how you know this isn't on a server, right? It would also be slow if it were on a server, but it'd be a different kind of slow. So I like to do and this is not running on top of an operating system, which is fun because we're used to Python running on top of an operating system. Oh, I have to spell system correctly. Can I spell system correctly? Echo, hello? Is that right? Right, that's what it should do, right? So this let me import the OS library, which doesn't have anything to do with OS, it has to do with command lines. And you're like, oh, a command line is an operating system. Okay, whatever, right? But this will also break with presumably C types, and it will presumably, nope, import C types. Import bit arrays. Okay, so that one it doesn't even pretend to support. Pyodid's cool. We should all use it more.
Just going back a bit with inserting 1 followed by, like OX 80. Does that have to do with endianness? Is it because you're just basically flipping it with the 1 going to the most significant portion, or no, this is not to do with endianness?
Using a hard-coded 128 is to do with endianness.
Okay.
And that's why it worked on my system, and it is not why I can say that you can do that for sure. It does not make sense once we are dealing with the bits inside of SHA to think of endianness, because we're not doing anything that is endian. It is endian agnostic. I guess like maybe the additions or something, right? But like, because it's not classical arithmetic, it's not making the same assumptions of how numbers work as other operations are. And so I don't think of it as being endian once you finish loading it. That could be wrong because of the additions. I'd have to think about it.
Gotcha. I'm just thinking of the Wikipedia pseudocode where it says 1 to enter, and then the final length in big endian, and then you're doing big endian to little w portions before you hash. So I'm just thinking, is that the same thing? It's just taking 8 zeros and 1 and just flipping it.
In the standard, it just says a 0. It uses the language of closeness or adjacency. And so, in that sense, it's not a numerical 0. It's just based on the positionality in the bit array. And so, because endianness refers to the encoding of numbers, it is not a number. It is a bit.
Gotcha.
Is how I would think.
On slide 4, I think, why is that expression equivalent to 0, not 512, instead of just being equal to 512? Point of k is to add something up to 512.
To a multiple of 512. So there exists n for which this is equal to n 512, or 512n.
So is n included in k or L?
K can, no. L can be much larger than 512. And so this modularity formulation is a way of expressing you can have any number of chunks, but each chunk must have to be of size 512, is the intuition here. This thing must be a multiple of 512. I'm taking another bite. Given any input, it is unlikely it is exactly a multiple of 512 bits. We add padding so that it is a multiple of 512 bits. then we assume the input is a multiple of 512 bits, and everything we do is easier. It's like we're cheating, but it doesn't hurt anyone. I have to point this out because it's weird. All of the variants of SHA256 I've seen, it matters a lot what index they use, and they don't always 0 or 1 index. There is actually an internal logic to this, and the way to explain the internal logic is you have to already understand that it works, and the only way to understand it is by using the indices. So it's, I don't know, it's recursively intuitive indexing. I'm pointing that out because I make indexing errors all the time. And I thought my slides were wrong. Of course, when I saw this, you see I make typos on slides, right? I was like, why do I one index that? It's like, no, you have to one index this. Okay, so this thing is one indexed. When I started testing my SHA256, I started on things that were very small, so I didn't have to do the recursive step. Of course you do that. Of course you get it working without recursion. Okay. Here is something that was helpful for me to think that I've referenced in respect to Leia's question, which is that the internal, like the inner loop, not the innermost loop of the hashing function, is we have a function that takes an M, a message chunk of 512, and a hash of 256, and returns a novel hash of 256. 768 to 256 every single time. This is a compression hashing function. We are throwing out tons of information, but we are using the information to cause each bit to change at high probability, right? Or at an expected or controlled probability, max. So here is the recurrence. We write this function. Mine was called like chunk or something, I don't know. Note we're one indexed. What is one reason we're one indexed? And here it begins to make more intuitive sense. The fractional components of the first 8 primes, we refer to those as H0 sub 0 through H0 sub 7. All 0 indexed. The messaging queues are 1 indexed because we put in message 1 at the same time as H0. Because H1 is the hash of message 1. Maybe that helps you, maybe it doesn't. But HI is the hash of message I. But the hash of message I also uses hash I minus 1. So on the initial message chunk, we denote it as message 1 because it produces hash 1 and accepts as input hash 0, and hash 0 is the hard-coded fractional components of primes. Okay, 1 indexed. Ari ruined everything by not having an Intel processor, so you can't actually use Aurora, which is rotate right long. And I don't know what you can use on your device because I don't have your device, so I couldn't test it.
I would like to point out I'm not the only person with that one back. There are at least 2 of us.
There's many more in Salem, but you were the first one to complain. And so the tallest blade of grass catches the blade, as they say. Right? So I was really hoping, and in fact, I found out a way to do this if I had access to all of your MacBooks. There's a thing that is strongly suggested I can get Podman to run x86 assembly inside a container on someone's device that doesn't have an x86 device. And since this is a very simple command to emulate, it should have been easy. But those of us that are cool and have Intel or AMD devices, yeah, can I hear it for the Intel AMD people? Can I get a whoop whoop? Whoop whoop? Whoop? No one? It's literally the only company holding up the entire state's economy, by the way. Okay. So like, just start liking Intel. Okay. Indy got fired by Intel because they're going through complete economic disaster. Never mind. Okay. Indy works for Thermo Fisher Scientific, which is where STEM PhDs work. Okay. The industry standard is to use standard int, right? Blah blah blah. Okay. SHA256 is old. It is so old, people are still using 32-bit values. So everything is with respect to 32 bits. This doesn't matter at all because the thing we're doing is scrambling. I'm going to introduce a series of ways to manipulate individuals or combinations of 32 bits. I'm going to tell you what the type of the function is because that's how I understand the functions. Now, where are these going to be used? These are going to be used inside of f, the thing I called f, which takes the 768 bits and returns the 256 bits. So each one of these operations I defined, the intent is going to be to take more bits into fewer bits in a way that all of the bits change. They're going to be unary, binary, and trinary. So I'm going to take 1, 2, or 3 32-bit words. And then I'm going to have these shift rotate operations. Those take something a little bit different. They take 32 bits, and then they also take a number that is smaller than 32. So that's a little bit goofy, and that's because you can't shift 32 by more than 32 bits. And you could shift it by the modular value of 32, but then just take the modular value, right? Okay. So these things are over 32-bit words, and these things are over 32-bit words and 5-bit words. Okay. Why do I call these words? They're collections of characters. The intuition is this simple. Another reason to call them words is that they're not really numbers. They're collections of symbols. So bitwise logical operations, we're going to accept 1, 2, or 3. I'm going to use the commonly accepted terminology that is also used by the person at IIT Bombay who actually understands this. U, V, and W. Why is that? Well, because we're using W for word, and then we can't use X because we already use X for integers. So we just go the other way, and we say U, V, W. How clever is that? I literally never understood SHA256, and this person comes in with this innovation. It's just like, just start before W and go forward until you reach W. I was like, okay, I'm going to use lowercase script n for the values that are smaller than 32. They're also bigger than 0. That doesn't matter. I think we're all familiar with bitwise complement, which is you take all of the bits that are 1s and turn them into 0s, and all of the bits that are 0s and turn them into 1s. An astute learner will wonder if you can do this in Python. And in fact, you can. And that's why you don't use Python for this, because that's ludicrously annoying, right? I actually do understand what's going on here, and I think I would be happier if I didn't, so I'm not going to tell you. The solution to this problem is to use C. I'm sorry. I wanted to teach this class in Python too. That's not true. I made up a class that you had to teach in C. Okay. Let me ask a series of leading questions. How many bits big is that?
Can it be anything? Because X could be one.
X has a bit length of 1 in Python. You can set y equals to bitwise negation of X. And we can see the bit length of y. It's 2. Okay.
So if you set X to a giant number,
Yeah, what do you
it'll
want?
still be 1.
What do you want?
Yeah. 2, 3, 4, 5, 6, 7.
I tried.
Yeah.
Before I just do this, does anyone want to guess what it's going to be? Yeah, how many binary digits do you need to express this?
12.
You think I hear 12? Okay. What's 2 to the 12th? It's 4096. Because 2 to the 10th is 1,000. So the shorthand is 2 to the 10th is 1,000. This is about 32 times 1,000. 32 is 2 to the 5th. 1,000 is 2 to the 10th. So This is going to be 15 or 16. I worry how you're going to debug your SHA256 code if you don't do enough powers of 2 for fun, right? I actually made the undergrads make bits on their fingers and then compute bitwise operations between them. And I'm not going to make you do that because you're adults, right?
Does that mean the not, is it doing the operation of flipping it and then just assigning it to a negative?
I have no idea.
Did you say you just want to explain it? You lying.
I'm both lying and telling the truth. I have an intuition for what it's doing, but there's one thing that fundamentally doesn't make sense, and this is the thing that I can't get around, is that there's 4 possible values of bit length 2, and I don't know how any of them would be negative 2. Now, I know what's happening internally, which is that Python's storing that thing in either 16 or 32 bits. But I have no idea how it decided that it has 2 bits worth of information when it has, clearly, a negative sign that is holding 1 bit of information. A 1, which is clearly holding 1 bit of information, and a 0, which is holding 1 bit of information. Because we can just simply type in 3 bits worth of information into Python and store it in 2 bits if this is true. And that makes me sad.
Is -4 also bit length 3 in Python?
Let's check.
Maybe it's not counting the sign.
It's not counting the sign.
Okay. Well, we've invented this sort of sign boolean.
Is that what we wanted it to be?
It would be consistent with what we got earlier. It's not correct.
Is it ever? Can I do this in Python? Does anyone know Python? My students all think I know Python because I use it all the time. And it's like, no, I'm reverse transpiling C. And you sprinkle in a little bit of Lisp from time to time, right? Like, we all know Lisp, so that's an obvious one. Okay, right. Okay, you know the binary bitwise operators because I taught them to you? Yes.
This can go back really quick. So when we're chunking our text or whatever we're dealing with, whatever data, we're actually kind of chunking it into whatever flag called -65 is, right? At any given time, and everything else is just that.
Always 512 at a time. And if we get something that is less than 512, we add stuff to it to get it up to 512.
Okay, so that 65 is for
A whole thing. So if there are many chunks, we need an
see.
extra 65 at the end. And sometimes that causes us to spill over and need an entire new chunk, and sometimes it fits in the rest of the chunk. And I don't ever have an intuitive sense for whether that's going to happen, but 65 is quite a bit less than 256, so it's unlikely to spill over. You know what all these things do? Inclusive OR, exclusive OR, bitwise AND. We got it? If I had to type this in Python, which I don't, but I'm going to. Oh, I have no idea what bitwise AND is in Python. Is it? Is it this thing? Okay.
Yeah, it is. Because you have to do that in hand sometimes.
You have to do it in pandas?
If you're trying to do like a conditional addressing inside a data frame, like normal AND does not work. You have to do bitwise AND, or it will give you like a completely inscrutable error.
Oh, because AND is... trying to figure out how I can see what AND is. That's not allowed. Do we think this is called? No. So because inside pandas, pandas backend is on NumPy arrays, and NumPy arrays are using C types, which means its internal types don't have method wrappers around AND. But the C bitwise AND is going to be a pass-through operator straight to C types, so you can still use it inside of a pandas data frame.
Gotcha.
Is my theory. I'm speculating.
Can you try something and set x equal to 4 and then do not x again?
That one?
No,
Or sorry.
That's crazy.
Yeah. And in fact, like these are the results you'd get in C. It's the recorded bit sizes that are completely unbelievable. Because they shouldn't put bit length in the language if it's going to behave like this. I think I didn't know you could take logs in Python when I started learning Python, because like I've never used a language that had logs built in before, because scientific programming is for scientists and I'm a computer scientist, right? So I just use bit length for log all the time, and it has these like really, really obnoxious behaviors. You know what these are. This is commonly used. So why do we introduce a new overloaded operator for bitwise XOR? We have to call it something. Right? Caret is like ludicrously confusing. This was common enough. That's, I think, the set operation for disjoint union or something. Does anyone know what that is? It's used in set theory. Anyways, it's fine for XOR. It's not too weird. I also really don't love calling these things OR. You see here I call it IOR. I would never say OR and XOR in the same context. I would always say inclusive OR, exclusive OR. I think it is underspecified to say OR if there's XORs floating around. No one else seems to think this. It drives me crazy. So, okay. Some of you may have heard of addition. This is where endianness might sneak in, and I'm not sure. I haven't gone through and checked for proofs or anything. We probably know how addition works, but this is not actually addition. This is some unbelievably cursed thing called modular addition. I remember we were doing modulos earlier. I remember how fun that was. The great thing about modular addition is you can add two numbers together and get a smaller number, and it's still positive. And that's awesome, right? That's really cool. And you can get Python to be exactly as goofy and silly and fun-loving as C using C types, which of course you cannot, under any circumstance, put into PyPy or Pyodide, but you can put it into our most beloved Python interpreter. Yes, paste anyways. I don't like how Windows doesn't trust me. Like, I know what I'm doing, right? I installed Windows. Okay. An astute student will notice that this number is smaller than that number. How did I pick these numbers? Well, there's 3 zeros there, 3 zeros there, and 3 zeros there. Oh, well, that's in between 2 to the 31 and 2 to the 32. And the uint type, I'm assuming, is going to be 32 bits. So I picked two things that were very close to the maximum value of a 32-bit value, added them together, and got something back that was a little bit less because my overflow wrapped around. But you don't have to believe me. We can check. I think I need to wrap this, probably. Does that sound right? No, we broke it. Wait, did we just learn something about precedence? Okay. Do you see this? Bit shift has equal or lower precedence than modulo. I never really get that. I was sure it was good for the same as exponentiation. What a horrific language. I can't believe they teach this in schools. Okay. Oh, good reason to use C. I'm so convincing. All of the other faculty are like, are you ever going to teach them something useful? Okay. C addition is already modulo 232. Something that was impressed really strongly to me in my second semester in C, third semester programming, is the Intro to Systems programming class at UChicago. It's taught by Ian Foster, who maybe actually invented the internet. I assumed no one read the internet, and then I looked up this guy on Google Scholar and read some of his publications, and I was like, this guy invented the internet. Anyways, he didn't seem to understand C that well. But he was really interested in this notion that you can't put infinite numbers on the internet, which probably affects you a lot if you're like doing the internet and you spend all of your life thinking about IP addresses, which you ran out of in 1977 and can't do anything about because no one wants to update the address space, right? So he spent a lot of time talking about how there's finite numbers of things, right? And that really stuck with me. And so I find it ludicrously annoying you can add two numbers together in C and get a smaller number. I'm just not used to that. In SHA256, this happens to be unbelievably useful because we're just trying to scramble bits. So it's actually nice. Like, what do you know? When I say I love SHA256, it takes this feature I find unbelievably annoying about computational, like the computer science version of addition. And it's like, oh, that's a feature now. That just makes the algorithm work better. Like, you would have had to take a modulo otherwise. And also, we're basically only ever going to be adding things together that are very likely to be using exactly all 32 bits. So you're always going to be getting the feature you want, which is that things that are too high are getting cropped off and things that are low are coming back in. It's just really cool. So you can run this in C. Should I run this in C? Do you all want to see me run C? Okay. That looked like a kind of pained thumbs up, so I'm not really sure what to think, but what do we do? We boot our most beloved operating system, Windows Subsystem for Linux. I am a bit of a Linux power user, actually. Wait, I could have done this in a Podman container. Oh, it's okay. How did it run twice? No. Look, it's the exact same features when I use the C features of the Python programming language. Does anyone want me to try anything else before we go on? There's a correct answer to that. You didn't get it. Oh, we're supposed to try a 16-bit integer. Okay. How do we do that? No problem. We remember all of the Vim motion commands. Yeah. Okay. Okay. Insert. I can't find delete on this keyboard. Okay. We want something that is in between 2 to the 15th and 2 to the 16th. How do we calculate that? Well, we know what 2 to the 10th is, and we know what 2 to the 6th is. 2 to the 6th is 64. 2 to the 10th is 1,000, so we're going to put in 64,000. No, we're not. We're going to put in, what should we put instead of 64,000? Would that be here? That's thousands. Let's do 40. Yeah. That seems fun. Ah! Why is I seem to be holding shift by accident. No, I don't believe in control. Wait, did you say control S?
I said you're doing capital X.
Yeah, no, but I couldn't figure out which one of my fingers was touching shift. Right? So like on my keyboard, right, there's two shift keys. And I have no mind-body connection with either of my two hands, right? So it's impossible to know at any given time which one of them is pressing the shift key, which is why I use Vim, the thing where exactly what you type matters every single time. Okay, I actually use Vim to impress people that don't care about what I think of them. Okay. Okay, that didn't do what I wanted. Am I not clever enough? Oh, okay. These are printing as %u is the format code for a 32-bit unsigned value, which means that even if I perform a calculation over 16-bit values, it will print out a 32-bit value, which means that this thing, the result of that computation is stored in 32 bits. Not to worry, I have an ingenious plan. I could either read the documentation, or I could just write a bunch of code that I don't know what it's going to do. And I love doing that one. So what do we do? After u comes v. So we'll do the v before u. And we're going to say v equals u plus u. Now, that v is told to be 16 bits. So the result of u plus u on that line should be stored in a 16-bit value. the result of the u plus u on the next line is going to be stored in a 32-bit value. So we simply come over here and we get rid of these pesky little u's and we put a v, and surely this will do what I want. Why does it take so long to compile? Ta-da! I've added two numbers together and gotten a smaller number using the power of a lot of different things. Do you all want this code? Can I select it? Did I post the Python I said I was going to post in here? Who's responsible for holding me accountable for all these things? I need an accountability buddy. Was it one of these things?
Is that X?
Which one?
Yeah.
Noted.
How did you get the prime started?
What's Discord look like? Oh, it was right there. Okay. Cool. Now let me see if I can remember what I was trying to think about at all.
Sorry, well, I didn't quite understand what you're doing with this last bit. What do you mean you can add two numbers together and get a smaller number?
So, in Python, the language cheats by letting you use as many bits as you need for the outcome of any operation. Or perhaps this isn't cheating, right? In SHA256 and in C, this is not the case. You have to specify how many bits you're working with. What that means, you might add two things together that if we had an infinite number of bits would in fact be larger. But somehow it has to decide that there's some result of that computation that fits in your fixed number of bits. It happens to do this using modulus. It doesn't matter how it does it. It has to pick some number. And this is interesting to us because it means in SHA256 we can add two 32-bit chunks together and never get back 33 bits. We can always assume that our 32-bit chunks will stay of size 32. And it's useful to assume they can stay of size 32 because we're going to be doing things like rotates and bitwise XORs on them. We want them to all be the same size. So that's the usefulness. I'm arguing, for the sake of arguing it, that if you're going to be using a computer that can only handle finite numbers anyways, it might make sense to develop algorithms and use computational techniques that benefit from that form of math, and to not try and force other forms of math onto the computer. This is the sort of almost exact negation of the enrichment lecture on libGMP, which some of you attended and which there is a recording of, where it's like, well, actually, we can jam arbitrarily large numbers into C as well. And I suspect Python is working on the libGMP backend. It's like, yeah, we can make numbers as big as we want, but we have to deal with all of these other things. And it's not always good to deal with all those other things. Sometimes you just don't need to multiply 10 million by 10 million. You can just multiply 10 by 10 and know that how many zeros are at the end of it, right? What I like about C and SHA256 is they let you be precise, and they don't tell you things that aren't true about the computer. But we do have to remember you can add two numbers together in a small number. That's non-intuitive. This really comes up. I wrote some for loops recently where my terminating condition was x less than 0, and I used unsigned values. And x will never be less than 0 with unsigned values. That is tautologically false. So it's good to remember these things, because you might think, oh, when I get to 0, then I want to stop. It's like, well, no, you have to be very specific about how you formulate that, because you cannot say less than 0 when numbers can only be positive. And the same thing's true if you do all sorts of other numerical operations, right? But I write a certain number of infinite loops because I forget that I don't use negative numbers in C, and I'm used to using them in Python. From there, this is the reference SHA256 implementation. I didn't look at it that closely. It seems to be correct. I've written my own, which I'm not publishing. Maybe I'll publish it. I don't think so. It's not that good, so it makes more sense to look at this one.
Just a question on
Yeah.
the addition to a smaller number. Is it happening because when you do the bitwise addition, it's just dumping off the bits that it can't have?
Yeah, it just
at the
slices
very
off the
last
top.
at end?
Yeah. I think we can make this visible in Python, so let's look at it. Okay, I have C addition in here. That's good. Okay, so I can do addition of, this is fine, right? Excellent. Okay, so let's take this value, x, and that's going, well, I know it was fine. X has some bit length, which is 32. That has some value. We can store that in y. Y is going to have a bit length. Presumably, Python's going to report 33 to us. If we take this and we take the lower 32 bits of it, we can actually look at that. So we can look at bin of y. It's this many. We can grab the lower 32 of it, and we can actually do that quite specifically. Is this the way to do the slice? And we can convert that back to an integer. Oh, it's slow. Oh, I guess I asked Python to do something pretty hard there, right? That makes sense. I'm transmitting numbers back and forth between strings. We don't know what libraries that's touching. That could be touching very, very inefficient code. You're not supposed to do things like this. I'm going to take the binary encoding of y. I'm going to chop off the top bit. I have to take 3 bits to get rid of the 0b. I'm going to convert that back into an integer of base 2. And it is going to give me this value. And separately, I can look at the binary form of that value. Please select. Okay. And see. We can also look at pin y. Oh, we'll start at 1 to offset it. We'll see these line up exactly. Right? We just take that one off.
Is that the maximum sign value for a, I don't know, bit size for a 32-bit?
The maximum 32-bit size is signed value?
Isn't that, or is this the unsigned? I'm just wondering why this is the cap.
Why this is the cap. This is the number of unique values that can be stored if you have 2 to the 32 bits. Or specifically, this is the number of unique values. I picked something that was close to that, but not more than. Okay. You all know choice and median because I made you write them. I think most of you did it this way. There's some kind of more efficient way to do it. You combine XORs or something. When I showed this in Salem, a few students noted they put logical or inclusive OR here. That might be fine. I don't know. I wouldn't assume that wouldn't work, right? Seems fine to me. Because the only thing you have to check is that any 2 of them have to be true. And so, it should be fine. Shifts and rotates are goofy because everything we've looked at so far, we've taken some number of 32-bit words and put it into an operation and gotten out a 32-bit word. We're now going to take a 32-bit word and a value in 0 to 31. That, to me, should feel odd. I would not usually store something that small in 32 bits. I would usually store it in 8 bits. I would store it in 5 if I were allowed, but there's no reasonable way to do that. At the same time, it is also unbelievably weird to use different sizes to store things, right? So we're probably just, in practice, going to store this in 32 bits. That's fine, there's nothing wrong with that. But we should recognize that versus all of the earlier applications, we were aggressively taking advantage of the benefits of using exactly 32 bits. We are no longer doing that here. We are now using the limitations of sort of our computational techniques where we just have to make sure that things aren't outside of the range of 32. You know what shifts and rotates are, but they're not too bad. We're only going to use right shifts. I have updated my terminology to standardize with Sarva from ITT Bombay. So I'm using SHR. SHR is also an assembly command. ROR, which I used in SHR, do a thing that is different in a way that is out of scope of this class, but they are not the same. They are the same on SHA256. You will not encounter the differences between them. So you say SHR for shift right. You can also call it a rotate. You can also call it a rot right. I don't care. A shifter perhaps, and then we also use rotate. And this is stylized here as rotate R. I got a lot of questions about this over the questions. Right, okay. This n, this little n, denotes how much you shift by. This u denotes the thing you're going to shift. It is unclear if you want to think of the right rotate as being a set of 32 functions, which is indexed by n, each of which is a different rotate, or it is one function that accepts 2 arguments. I don't care. It doesn't matter. But the point is we're going to have different types of shifts. Now, we're not going to use that many types of them because we're going to combine them in specific orders, right? So actually, you only need these 10 unique forms of rotate. So you could, if you were making an SHA256 hardware accelerator, write circuits that do each of these very, very quickly. And in fact, that is done, and that is how you mine Bitcoin at a fast enough rate to make money. And you can do the same thing with the 2 shifts. Something that jumped out to me about these shifts that I would not necessarily expect you all to worry about that much, these values are both less than 32. That's relatively unlikely to have happened, or they're both less than 16. These are small. Why does that matter to me? When I shift, I introduce mandatory zeros. This is the only non-conserving operation. Adds, you keep roughly the same number of 1s and 0s. XORs, you keep roughly the same number of 1s and 0s. Inclusive OR, you add 1s, right? If I inclusive OR 2 and, I don't know, I'll do this, 2, then I end up with 3 bits. So I'm adding bits over time. I needed some operation to keep my balance of 1s and 0s correct, and it was a small selective removal of a few bits at a time using the shift right. So we're cutting off 3 bits, which on average holds 1.5 1s, and 10 bits, which on average holds 5 1s, at each one of these iterative steps that applies the lowercase sigma operator.
Are we supposed to understand how this applies to the SHA256 algorithm?
This is a component of the SHA256 algorithm.
So right now, are we working with keywords, the 16-bit?
Each of these are 32-bit words.
32-bit words, and there's 16 of them, right?
I think it's unhelpful to think that there's a fixed number of them.
Okay.
This is going to happen in a loop over something called the message schedule array, which is populated at a later stage in the algorithm. We are defining these as macros to use inside a later loop. We are defining them as macros in similar ways to how we defined choice and union. We just want to have the operations around the constrandle bits in certain ways, and then we will apply them to the message schedule array. Message schedule array.
So for those of us that are slow like myself, we are taking, right now we're processing that 512 chunk, and it's going through this jumpler.
Yes.
Okay.
For each 512 byte chunk we process, we will apply each of these operations many times to different intermediate values that we make while looping over parts of the 512. The 512 is divided into some large number, 64 32-bit chunks. And each one of those 32-bit chunks is looped over, and there's a variety of local variables that are upper and lowercase sigmoid. Okay. Maybe this will answer your question, we'll see. Hash computation is 4 steps for each 512-bit chunk. So this is after we've padded, right? We are only working with 512 bits at a time. We've made that simplifying assumption. That simplifying assumption is of great benefit to us, right? The first chunk comes in with the pre-computed hash values. Each successive chunk comes in with the hash value computed on the previous chunk. All chunks share these pre-computed k values, which are the fractional components of the square roots of the first 64 primes. I think these things are called the round constants. Yes, those are right there. We needed to have some numbers around to XOR with something. So the same way we had initial hash values, we have round constants. So there's a large number of constants that are defined. The components are set the message schedule array. That is a 64 array. That is 64 by 32. So that is some large number of bits. I don't know. I can't do this. I'm cooked. Okay. No, I should have to do it. I would make you do it. Okay. So 64 is 2 to the 6th, and 32 is 2 to the 5th, so it's 2 to the 11th, so it's 2048. Okay. It's so late. What time is it? How long have we all been awake? Yeah. Okay. All right. Set working variables. Okay. I really perceived of this in terms of like a number of lines. I had some array that stored 2048 bits, and I threw a bunch of stuff into it. And I'll describe that process in a minute. Once that stuff was in that array, then I went to later lines of code. Those lines of code referred back to the 64-word array. They also referred to the round constants. They also referred to macros I wrote on a previous slide. And what they did is they maintained 8 word-sized variables, which I think I called A through whatever the 8th letter of the alphabet is, which is probably H. And I just had local variable names for them. Each of them was 32 bits, and I was doing manipulations on them. To me, it was very strange that these were not in an array, that no one else put them in an array, so I didn't either. And then we have the main loop, which is going to look at 1 and 2, jiggle things together. And when that's done, the values in these 8 words become the new hash value. So whatever is left in here when we're done happens. We're going to loop over this 64 times, one for each word in that array. I know what you're thinking. You're thinking, Calvin, how are we going to populate the 64-word array when we only have 16 words? You said 2048. That's 4 times bigger than 512. Not to worry. I have a plan. And this is the plan. I think it's a pretty good plan. This slide looked way more confusing than I thought it was going to look when I pressed next. I was like, the next slide is going to make this all clear, right? Let's point out some things that are helping us here. The first 16 are easy. Why are they easy? The first 16, or the first 512 bits of our 2048-bit array are exactly the 512 input bits. You make no manipulations at all. Maybe easy is a strong claim, but it could be a lot more complicated, right? I implemented this as a mem move operation. Pretty simple. So, do I want to read all that stuff? No. Okay. I take my first 16 entries in the message schedule array, which is 64 32-bit values, okay? Once I've loaded in the first 16, I go over the remaining 48. That can't be right. What's 64 minus 16? Is it 48? I need to practice. Okay. I was doing like Sudokus every day for a while. I was doing crosswords. I was writing a C programming language for fun. For a while, I was doing cardio, right? I was like superhuman, right? And then I got sad because I listened to emo music. Okay, we're getting a lot of help here. This thing is not bigger than 16. This thing is not bigger than 16. This thing's not bigger than 16, and that thing's not bigger than 16. So as soon as we load the first 16, we can recursively populate the remainder. So, looking at the 17th, no, the index 16, which is in fact the 17th entry of the array. Well, I take the first word, which I just populated, and that's also the first word of my message. I defined this function on a previous slide or on a previous line of code, and I apply that to the word immediately after this one. You'll notice that this is a way of combining two adjacent words, right? This is bit scrambling this word and adding it to that word. Then I do roughly the same thing with something 2 and 7 prior. So this is a simple loop. It iterates 48 times over the 48 unpopulated elements of the word array. This is very easy to see in the JavaScript implementation. You should pull up the JavaScript implementation. If you're confused right now, I'm going to show you where it is so you can find it. Am I? Okay. Which one of these? No, I don't want to auto run. Okay. I want to go back. Can I go one step forward?
It's the red button.
What's the what button?
The red button. Go one step forward.
That's the one step button? That's not intuitive to me. Red is bad. It's still auto running. I should sleep more. Okay. Wait, no, you said the red button is not auto run.
Yeah.
I can do this. Okay. We copy in the first 512 bits, and then the other bits are uninitialized. The JavaScript is using that lighter color to denote, well, it is showing zeros there. In practice, there is no information there at all. And if I click this once, it's going to go forward. Have you used this?
Yeah, I based my entire implementation off of.
Oh, did you like it?
Yeah.
Okay, cool. All right. So we're going to populate the message schedule array one entry at a time. There are 64 such entries, right? Blah, blah, blah. I don't know. It's not that hard, right? But you'll see it's grabbing information out of prior points in the array and populating later points. These are the sigma operations, presumably. I don't know what they are. Oh, I'm live streaming. What's up, YouTube? All right. You gotta say it, right? If you say it, you don't get the likes and the comments and the subscribes. I describe myself as a content creator with a part-time job as an assistant professor. I just do it for my fans. We're going to set the working variables. I do hate this. I think this should be an array. I also think it's really annoying to use a working variable h and set it to the value of h superscript open paren I-1 close paren subscript 7. But Sarva at IIT Bombay did this, and I'm not about to argue with that person because I've never seen anyone else explain SHA256. So I actually did in fact understand this, and I'm unwilling to change it because this is the only way I've ever understood it. And in fact, in every implementation of SHA256 I've ever written, I dutifully declare 8 different variables, all with exactly these names, and then my code works mysteriously, and I don't know how or why. So, 8 local variables. What does this look like in C? Well, I said uint64t, and then I wrote a, comma b, comma c. Right, that's all. And then you can assign that initially on whatever the hash is that gets thrown into your function, right? So my function accepted, they were coded as uint32t stars, right? And one of them was called h, and one of them was called m. And I just wrote a bunch of equal signs. It felt very inefficient. Okay. The main loop, which is denoted, is this going to skip forward exactly 10? Okay, right. So, after we finish populating our message schedule array, we're going to grab the round constants and we're going to have to start doing other stuff with them. And the operations we're going to do with the other round constants are, you see I'm stepping through this and the working variables are updating at each stage as I go through, right? I'm referencing the round constant, which is pre-computed, and then I'm referencing the message schedule array, which I determined in the previous step. A through H are changing each time, and they're changing according to the sigma operations and the majorities and the choices that I designed. Right here's sigma 0. Right? Okay, so each time I click this button, we look at one entry in the message schedule array. That's the next loop, right? We're going to loop 64 times over the message schedule array. At each point in the message schedule array, I'm going to look at the message schedule array, I'm going to look at the round constants, and then I'm going to look at my local variables, and I'm going to update them as follows. I'm going to compute two temporary values. They are going to look at the round constants and the message schedule array. And otherwise, they're only going to be over the local working variables, right? So 8 working variables commingled with a round constant and a message schedule array value, or vice versa, whichever side you imagine it on, right? I'm going to loop over this 64 times, one for each message schedule array entry and one for each round constant. And at the end of that, A through H will be set equal to some value. This is 64 reassignments of 8 variables with the calculation of 2 temporary variables. That's all. It's a for loop. It's like 10 lines. Right? You calculate this in one line, you calculate that in one line. This is 10 lines of assignments because we don't have multiple assignments. This is the part I wished I was writing in Python, because I would absolutely write this in one line in Python. Is that wrong? Is that unfathomably based? Is that goated? What's up, YouTube? Okay. Feel like I should be on Twitch. Twitch.tv/Professor Calvin. Okay. Then you're done. That's actually all. I tricked you. I told you there was going to be a fourth step. The fourth step is being done. That's my favorite step.
The fourth step is making sure that you have 2 spaces after the digest, because otherwise you don't pass the test.
Really?
Yeah.
That's good to know. Who wrote that tester?
I don't think it's a UCOM. I think it's weird that the SHA256 sum just has 2 spaces after the digest.
The SHA256 sum is like not my favorite command. It's not the one you're supposed to use. There's like one in OpenSSL that's the one you're supposed to use, but I have to tell you to install OpenSSL to have it. Well, anyways, it worked fine on my machine. Okay. So as much as I would love to stand before you and do binary arithmetic in my head for another half hour, which is in fact the other half hour of lecture that I would do right now, do you want to like ask me any questions and work on this for a little bit while I'm here, and then you can like filter out at your own speed? Cool. Yeah. This is too bright. I have to. Okay.
I feel like I lost you somewhere after you defined the X forward stuff.
Okay. Were you good here?
Kind of.
Okay. So, I'm thinking of this. Let's pretend we're software engineers. I wrote a bunch of functions. These are the functions I'm writing. Perhaps there is a Java interface that implements these operations, right? So someone has just given me sigma 0. I don't care what happens inside sigma 0. We achieve encapsulation on a wide range of bitwise operations, okay? And we will now never consider these bitwise operations ever again except to call them as functions.
They're just helper functions.
They're just helper functions or macros. Does not matter. I don't recall if I used helper functions or macros. It makes literally no difference. Okay, so I've written a bunch of helper functions. Okay, now I'm going to write one big function that's going to have 2 or 3 for loops in it, depending on how you think about it. And those are going to be these for loops. I'm going to set the message schedule array, and I'm going to have a main loop. And you could argue there's other loops in there. The message schedule array is going to be populated by the message chunk, which I'm going to copy into the message schedule array.
And this is still just for one.
This is for one chunk. Yep. Okay. So I take my 512-bit chunk and I copy it in the message schedule array. And then I go down the remaining 48 things and just take things from earlier lines and put them in later lines. Okay. And when I'm done with that, I have 20 48 bits. And it just so happens I also already had a separate collection of 20 48 bits over here that I'll call the round constants. And I don't think about those, they just exist. They were provided to me, I calculated them in Python and then loaded it into C. They've been there since the dawn of time, whatever, they just exist, right? And they're never changed. The message schedule array, I had to do all this to calculate. And remember, there's lowercase sigmas there, but I don't have to think about those anymore. Someone else already wrote those for me. My subcontractor wrote those. My undergraduate researcher this summer wrote those for me. I'm assuming they're correct. They're not, right? Never hire an undergraduate. Okay. They keep like getting sick or something. I was like, sleep enough. Okay. We're ones to talk. Okay. So you have your 20 48 bits, and you have your other 20 48 bits over here, and you start the second for loop. This second for loop also runs 64 times. And what it does is it has 8 variables, and each time it runs through the loop, it looks to the left, and it looks to the right, and it combines these variables in this following way. It computes 2 temporary variables. Now, this thing looks sketchy. What it really is it shifts all of your variables over by 1. Can I do this with my hands? No. Wait, yeah, I can. Okay. It shifts them over by 1, like so. And then this t value becomes the new replacement value. So I actually throw this out, but it becomes an entry to t1. So I compute some new value, which becomes the new a. And I make a slight modification to the 4th value. So I like turn it up or something, right? And we keep doing this over again. We shift everything over 1, which is not the easiest thing to do in the world. I know, I'm flipping people off. I do this a lot in this class. Then we throw this away, we do some manipulation over here, and we manipulate this value. And so you just sort of shift repeatedly over these 8 values, doing these minor update operations to them. These are all single line, single equal assignments. And you do that 64 times, and then there's different values in them at the end, and that's the new hash value. Whatever is an A through H at the end is the new hash value. Now let's not do this on my fingers, let's do it on the algorithm. Okay. We have populated the message schedule array. Do you feel okay about that, or do you want to look at that again?
I mean, I generally get it, maybe.
Okay, cool. We put in these bits, you can tell. I put in a small amount of information, right? Relatively few bits. And so, is that, would bigger help, or do you want to see all of it? I can zoom in or not. What do you think's easier? Okay, great. So that is the 512 bit chunk. The higher.
Through W15.
Yep.
That's the first one.
0 through 50. This is the padding. That represents that there's, I don't know, 60 or something.
3 through 15 is the best.
Yes. And you see the leading 0.
Right. The leading one.
Yeah. And so then all of the rest of this is populated by looking at those earlier values, performing operations that we're going to figure out what those are. So 32 is based on some things before. It's saving those conditions.
Gotcha. So, sorry, so this W53 goes to 64?
Yep. It's just upstream.
Okay.
And so does this. These are given to you. These are round constants. I gave them to you in the assignment. Okay. What's going on right now is we are at the 25th pass through our 64 loops. We have our working variables, each of which is equal to some value. This stuff might look scary, but actually our undergraduate researcher got all of this to work this summer. So we don't have to think about any of the things that we're doing. This is just magic. It just works. And the way it just works is we wrote 10 lines of code. We calculated T1 and T2. And then we update A, B, C, D, E, F, G based on having those values calculated. And so every time we do one more step, oh, I was sure that was going to be autoplay. Okay. Every time we do one more step, the code our undergraduate researcher wrote for us this summer computes 2 new temporary values, and then all of our values in A through H slide down by 1, and some of them are modified. D gets something added to it, and A gets something added to it, but otherwise we just shift them down every time. And so we can see that the value in B starts with 3 zeros followed by a 1, and the next time the value in C starts with 3 zeros followed by a 1. I think we get that again in D, but when you come out of D, something gets added to you, so we might get a different value. And yes, so the 3 zeros followed by the 1 disappear in E. But we can also keep tracking this value through. That's going to be 3 1s followed by a 0, and you see it shift down, 3 1s followed by a 0, 3 1s followed by a 0, 3 1s followed by a 0. When it gets to H at the end, it doesn't go anywhere. It goes into one of the temporary calculations, which are defined over here, and ludicrously confusing, and I would look at the slides rather than this for those. But we're going to calculate some intermediate values, and we're going to load that into A. So there's a novel value in A each time. By the way, you can mouse over this and see hex, which is maybe 100 billion times easier to understand than binary, depending on who you are. And 64 loops. Each time you do all the same updates. We don't worry about this stuff too much. We've encapsulated it. It's inside macros. And we just keep updating the A through H values. And if I will go, is that autoplay? These values at the end are the output values of the resultant function. And so these are the new hash values. And presumably, this thing ends in 13, or starts in 13. I don't know the exact magnitude then, I guess. Let's see. Oh, that's, wait, this is hex, right? 80. Is there an 80 in there? I don't see the correspondence immediately between this value. But these terminating working values should be the values you return. I don't have my solution here. Oh, I should submit an SHA256 here. Okay. You define a bunch of these things up top. These are provided. A through H. This person's using IJ for something I don't know what they're using IJ for. Load in the state. Oh, this person's not doing what I want. Oh, here it is. Right. 10, exactly 10 lines, right? 63 through 72, right? Each of A through H are assigned to a new value. Why do we go in this direction? Because we set B equal to A, so we want to assign it according to A. So you always start at the end, you always end forward. Calculate T1 and T2. You shift everything up 1, and then you do 2 additions. And so that's the sort of second stage after you set the message schedule array. The initial setting of the message schedule array is not bad at all. It's used here with an MSAT, right? So this, right. This is the message schedule array. There's a 16-bit loop. That should be an M loop. This is lazy. You should not write code that way. It's fine. I can't stop you. And then this is the remaining. When this loop starts, that I is equal to 16. It's the left that loop at 16. And these are the sigma functions that are populating the message schedule array. The message schedule array, which is referred to right here, inside the later loop. I'm going to stop showing you this because then you're not going to be able to write your own code. But I very much believe that it is. Oh, there's 10 lines of assignments. That is what it is.
So, about not being able to write your own code. I think it's an interesting conversation, and it's been like kind of my struggle with this class, because in order to understand what's actually needed, like for me, those slides aren't as descriptive as they are to you. What makes more sense to me is that code. So in order to write the code, I have to read the code expected of the code. And so I'm not sure if the learning, at least going from engineering to computer science, which I think a lot of us are trying to do, is in reasoning about how to shift the bits. Even though that's a great thing to understand, I think in even reading the code, you have to understand how those bits are being shifted. But then it becomes an exercise in can I read C? And put it into a file that you will read, which I'm not sure is what you're going for.
I don't think I'd say that's not what I'm going for, right? Correctly encoding these interfaces is like an independently valuable pursuit, but it is not the sole learning engine, right? But in fact, I did take time out of this class to train containers for a reason, right? And to preserve interfacing and show automated testing scripts and all of these manners that I think are useful, right? I think my position is that if you can get someone else's C code to run on your own, that is like an independently worthwhile pursuit, and that's something that I've like spent a lot of time doing in my life. That's not like the only way to find value from this class, right? You could separately try and write this without starting with someone else's C code. I suspect, and actually I know, because I tried to run that code, that it does not work. And it doesn't work for the envious reason. It assumes you're on a computer, or the only, or not the only hard part. By far the hardest part of this assignment for me was not handled by that code. I had to solve something I thought was dramatically harder than getting anything else to work, which is why I made a whole NDNS lab about it, which is why for this class, without having time to do NDNS lab, I suggested you use a library to solve that problem. But in fact, even just knowing where to use that library is like non-trivial, and it's much easier with this because you can just look at bits. Right? But I think getting other people's code to work is like pretty useful and like a pretty big part of writing C. I think what I don't want to do is make it impossible for you to do this on your own if you want to. And for that reason, I don't want to use, I don't know, something very close to an answer key as the problem description. But I would certainly not discourage you from looking up whatever you need to feel like you can accomplish the assignment. And so I have, and I linked a solution to this assignment in the slides, right?
I feel like what my brain wants, and maybe this is bad, maybe it's a crutch, is like something one step above pseudocode, and then to be able to translate that, because I'd be learning the algorithm and translating this human readable concept into the C language, which feels attainable and something that I could do in a reasonable amount of time.
When you say one level ahead of pseudocode, which direction do you mean from this?
Closer to human language than code.
Closer to human language? Okay. Well, this is wrong. This is just random constants. Okay.
I don't know if other people feel that way, but I felt like it was worth saying.
Yeah, no, it's good to have input, and regardless of what other people are saying it. And if other people are saying it, you should say it now. But it is not immediately obvious versus the Quarto markdown, which is not the same as the HTML document. I think I'm perceiving myself as one level ahead of this, one level closer to natural language, and so I would have to think about a way to solve that problem. I essentially took each of these code blocks and wrote my own descriptions of them for the slides, right? And so did Sarva. We've done the same thing. Have you taken a look at this?
No.
Take a look at this and let me know what you think, and maybe that'll be the most helpful thing. Because, in fact, this is pretty far removed from pseudocode, right? Such that something is a multiple of 512. Like, I don't know, that's not an easy line of code to write. That's several arithmetic operations. And this is such that the bits in the, like, this is a description of a data structure, right? Like, we can argue that's pseudocode or not, right? So it would be helpful to know whether this feels excessively high or low level to you.
I think that the problem is not like the understanding of what that line is saying,
Mm-hmm.
but the understanding of it holistically.
Mm-hmm.
And so it's hard for me to answer the question because if someone were like, represent this in code,
Mm-hmm.
might I? Maybe, but would I be able to put it into the SHA256 algorithm correctly? Maybe not, which likely means there's some other knowledge gap.
Mm-hmm.
And I think it's probably trying to reason about bit manipulation and what's happening holistically at the same time. Because even though this isn't a lot of lines of code, there's actually quite a bit that's happening.
It's several hundred lines of C, which is pretty significant. I guess I don't know how many lines of pseudocode this is. I think my solution was around 200 lines of code, and I generally assume I can write things in a pretty small fraction of what students can do, right? I budgeted this as a 500 line of code assignment for y'all. That's what I was expecting, and some of you will come in well under that, and some well over. Everyone will have roughly the same number of live lines of code, right? I think in lieu of a direct response to your question, I'm going to advocate for the specific formulation of problems I have in this class, which is end-to-end executables. It is, to me, a core learning objective to put you in a position where not only can you write a function in a language that does a thing, but that you can generate an executable which does a thing. And this is dramatically harder. I wrote RSA in C in like not a very long number of minutes last week because I needed it for something. And I have spent several days trying to get it to output the public and private key, which are things we'll learn about in a few weeks, in a format that is accepted by any existing SHA algorithm, or any existing RSA algorithm. And RSA, at least until 2 years ago, was the most popular cryptographic algorithm in the world after this one. I can't figure it out, right? And I can't figure it out because there's no documentation anywhere in the world, and I'm reverse engineering cryptographic technologies, right? This is like I think like a pretty useful skill to do because I don't perceive it as hard to debug anything else anymore, right? When I first learned Enigma, I brute forced it, and I just wrote my own spec, right? It was easier for me to do that than to read someone else's code. I don't think that we need to be that extreme, but having assignments that are implement this thing that is already on your computer so you can check to see if your answer is right or wrong, I think there is an independent value to that, in that you can check to see if things are right or wrong immediately and get that form of feedback. And it also prevents what I see students do. I saw this with a student today who asked me if my grader was wrong because it said their code was always returning zeros. And there was no SHA code other than return 0 in all cases. And I was like, no, you didn't do the assignment, right? It is useful to have these things that keep us accountable to like achieving a certain form of executable. And then the last thing I would say, and I think this is useful, is like when we're dealing with things like binary bit encryption, getting our bits to come out in the same string or ASCII or email or file format or whatever format is an existing tool is one of the only ways to make sure we're actually understanding the bits correctly. Because there's no real way, and I found this very quickly with Endian. My C implementation was telling me bits were stored in my computer in a way other than they were, which I could demonstrate by I could like shift them left and saw they moved right in the print statement. And that made me really uncomfortable about claiming my implementation was correct until I got the exact same solution as SHA256. And I don't think I learned the thing until I had the same output as SHA256. I think essentially I was like doing something inspired by SHA256, or not fundamentally understanding how to move bits around in the device. And so I would advocate for it from that reason. in terms of difficulty, I understand all of those things are difficult, but to find tasks of interest at lower levels of difficulty might also be like relatively unappealing for a variety of reasons. Like maybe it makes more sense to try to spend the entire 14 weeks of the semester implementing SHA, if that's what it takes, than it is to try and do a bunch of smaller tasks that are less interesting, especially given how powerful SHA is as a cultural force. Right? It is used in most other cryptographic algorithms as well. Right? So, anyways, think about those things and get back to me. Like, if it is completely reasonable for you to disagree with the way that I am conducting assignments, or to say it doesn't work for you and ask for changes, and I will do my best within that environment. But I am going to appeal to you on the basis of the end-to-end thing specifically. I was not forced to do that in undergrad, and then I had to teach myself later. And I just don't think that was a good way to do things.
Yeah, just a quick comment, because it's almost time, but Leanna, did you look through all the pseudocode? You said no, right?
No, but I have looked at a lot of other pseudocode,
Mm-hmm.
but I will look at this specifically.
I was just going to make a comment that
Oh, yeah. If you have another one, you can send me what you've seen.
this pseudocode specifically made me understand this and implement it, and I think I understand it better than Enigma. The only thing that took more than, like, this is basically one-to-one from what I got. The only thing that was more complex than what's written here was the pre-processing pad. That I made a mistake to try to do it at the end, not the beginning.
Yeah.
And it's, it's easier said than done for pre-processing and padding a file. But other than that, it did seem like a very much one-to-one implementation. That's what I'm asking.
I do
Something
think, yeah.
And I definitely would recommend just this pseudocode specifically, looking at it. I thought this one did a good job.
I like Wikipedia a lot more than other places, and including .c files. Right, there are .c files that were less easy to follow than this. But also, like, that's not to say it makes sense to you. There's a lot of, like, this is like an unbelievably cursed way to write a for loop, right? There's just no justification for that. And it's like, it's okay to not like that, but I think like using write rotate as an infix operator, like, I don't know, there's some goofy things in here. It is true that it's correct, and it is true that I could write a Python front end that turns this into C, right? That is possible, I could do that. But I wouldn't do that, right? Like, this is an odd way to write code.
Just to close the loop for now, I think my main takeaway is that getting things to run and getting things to run in the context of your tester is in some sense at least a partial learning objective.
Mm-hmm.
And to kind of focus on that instead of trying to focus on staring at a blank screen and coming up with SHA256.
Yes. Mm-hmm.
Okay.
I think one of the things I said, perhaps I didn't say it in this class, there were many students, at least in Salem, who were of the impression it was really important to get Enigma right, and that it like didn't really matter if they like had a C development environment on their computer, or like very basic things, right? And so they would like go in online GDB, or in fact you can write code in Google Colab, and they would like write really, really atrocious C code because they had no way to test it, right? And then they'd be like, oh, I like ran out of time on this. And I was like, well, you could have, instead of spending 8 hours writing code in a like nightmarish environment, spent perhaps those entire 8 hours getting the tester to work and understanding the tester. I regard the tester as a considerable portion of the documentation of the assignment. I think it is the only correct form of documentation of the assignment. It's the only thing I can verify that it adheres to my solutions. I write the assignment instructions based on my solutions, but I don't consider myself to be good at that, right? But the testers are exactly correct. And most of the time in my life when I write code, I do not have assignment instructions, right? But I very often have a series of inputs and outputs I can test. And often those are specified in ways that I find frustrating until I am done with the assignment, and then I realize why they were formulated that way, right? So I would appeal to you, think more about process, think more about testing, think more about scripting, think more about translation. And these things are, SHA can become trivial really, really fast if your tooling is good enough. right? If you can automatically compile this thing into C using a few Python scripts, which is not a particularly hard thing to write most of the assignment by itself, right? And that might be a more natural way to do it. And I think you're a JavaScript programmer, right? You can do all of these things in JavaScript, right? It's clear how to process text in JavaScript in ways to make a lot of the assignment a lot easier.
Okay.
On this assignment, I spent most of the time writing the tester, and then when I had an automated tester, I found my bugs instantly, and I fixed them. Yeah. Cool, thank you. And good luck on the assignment. I think you'll enjoy it even if you don't finish, and you'll finish someday. This will live rent-free in your brain until you get it. I mean, I found out about this stuff 12 years ago, and I finished it this summer.
It was because I was misunderstanding how to construct a message schedule. Because I didn't realize that there were trailing.
I think I'm a vampire.
And because I was comparing my message schedule to the one